We often take the speed of light for granted, assuming its arrival signifies an immediate and current reality of distant objects. Yet, every photon that enters our eye is fundamentally an ancient traveler, carrying news that is already millennia out of date. It feels strange to stand here in the present moment, illuminated only by the ghosts of stars that may no longer exist. Perhaps the concept of now is merely a comforting illusion, a psychological shield against the overwhelming archive of the deep past. The light from the Andromeda galaxy, our nearest massive neighbor, began its journey across space almost 3 million years ago. What events transpired on that world when this very light was just beginning its long, unhurried trek toward our telescopes? We feel a strange kinship with those moments, a shared history with stellar explosions that happened before our ancestors walked upright. This ancient light is the universe's memory made visible, a slow accumulation of everything that has ever occurred in creation. A quasar, billions of light years away, shows us conditions that existed when our solar system was merely a cloud of dust. How can we possibly comprehend such vast stretches of time, where our entire recorded history is just one fleeting second? It evokes a sense of profound humility, realizing that our lifespan is a microscopic flicker against this grand, illuminated chronicle. We are living in the afterglow of history, receivers tuned to a cosmic broadcast that never stops transmitting the events of yesterday. The speed of light, approximately 299,792 kilometers per second, acts as a fundamental temporal barrier, a relentless governor on observation. If this universal speed limit defines how far back we can see, what other limits govern the past we can never truly touch? It is a lonely endeavor. This act of peering into the dark, conversing only with echoes that have long since passed their source. The light that guides us is not a pointer to what is, but a patient map showing us where we have been. When we observe a supernova remnant, we witness the violence of a star's final moments, millions of years after its demise. This celestial wreckage, still blazing across the gulf, begs the question, can creation truly be separated from the moment of its ending? I often wonder if the builders of the first stone monuments felt this same connection to the dust under their feet. Our reality is constructed upon layers of arrival times, a silent, staggered concert of events unfolding across the great expanse. The faint microwave background radiation bathing us right now is the oldest light detectable, a whisper from the universe's infancy. That ancient light carries the imprint of the universe when it was only 380,000 years old, barely out of its cradle. To look upon that radiation is to feel the warmth of a time before stars, before planets, before the very concept of existence as we know it. We are intrinsically bound to that beginning. Every atom in our body is a direct descendant of that primordial, incandescent event. In deep space photography, we see galaxies as they appeared during the time of Earth's early formation, a visual time warp. If we could somehow travel at the speed of light, would time cease entirely, leaving us suspended in an eternal moment of observation? Such a journey would mean leaving all human connection behind, becoming an isolated witness to the universe's ongoing, eternal performance. Perhaps detachment is necessary for true understanding. Only by surrendering our attachment to the present can we fully embrace the immensity of history. The James Webb Telescope captures light that has traveled for over 13 billion years, offering views into the cosmic dawn era. Are these the first lights that ever illuminated the void? Or are they merely the first lights that happen to reach our fragile instruments? It requires a quiet mind to accept that the most beautiful things we see are inherently the things that are already gone. The beauty is not in the object itself, but in the faithfulness of its departing message, preserved across the vastness of time. When we look at Proxima Centauri, we are seeing our closest stellar neighbor as it was more than 4 years in the past. This proximity should give us comfort. Yet the delay emphasizes the terrible gulf that separates even our nearest cosmic companions. It reminds me of an old letter, finally opened decades later, carrying the emotions of a person who has since completely changed. We are constantly reading the universe's correspondence, piecing together a biography written in the slow, luminous ink of departing light. The concept of lookback time is intrinsic to all astronomical studies, forming the basis of our entire cosmological timeline. If we could see the present universe across the entire expanse, would we find a landscape utterly unrecognizable to our current models? It's a difficult truth to hold, that the things we study most intensely are forever locked away from us by the constraints of physics. We learn patience not from meditation, but from the light itself, which obliges us to wait for every single piece of information. Consider the gravitational lensing effect, where mass warps space-time, bending the light from objects far behind it toward us. These cosmic lenses offer multiple images of the same ancient event, creating a composite photograph spanning different moments in time. It is like witnessing a single event through several windows, each showing a slightly different perspective from a slightly different age. Even distortion reveals beauty, confirming that reality is rarely singular. It is often an accumulation of mirrored, delayed perceptions. When tracing the path of a distant photon, we are tracing the geometry of the universe itself, a map of gravity and history. Could a civilization far advanced beyond our own perhaps navigate these light paths, reading history forward and backward along the same beam? The thought of such mastery over time is dizzying, yet it confirms our own primitive, one-way journey through the cosmic river. We are all moving forward, but the light we see is forever retreating, a constant reminder of the irrevocability of what is past. The faintness of faraway light is not only due to distance, but also to the subtle absorption by intervening interstellar dust clouds. Does this dust carry the chemical signatures of those lost eras? A physical residue left behind by the stars that have already died? It is comforting to imagine that even destruction leaves a trace, a small, tangible remnant lingering in the quiet darkness between systems. Every obscuring veil of dust is a momentary pause in the narrative, a place where the universe catches its breath before continuing its epic. The color of light shifts slightly toward the red spectrum as it travels across immense cosmological distances, known as cosmological redshift. This reddening is the fingerprint of expansion, the visual evidence that the space itself is stretching and diluting the ancient signals, like a beloved voice slowly fading on a long-distance call. The color drains away, representing the gradual loss of immediacy. In this process, we see that even the most fundamental aspect of existence, light, is subject to the persistent pressure of time and distance. This observation allows us to map the universe's expansion rate, calibrating our understanding of the cosmos's ultimate fate. If the expansion is accelerating, as evidence suggests, then future generations will see a universe that looks progressively emptier and colder. It gives a sharp, poignant edge to our current observations, Knowing that we may be living in the universe's most illuminated era, the light reaching us now is not just history. It is a fleeting gift that will soon be taken away by the turning of the cosmic wheel. We rely heavily on standard candles, like type Ia supernovae, whose predictable peak luminosity allows for accurate distance measurement. Do these stellar explosions, occurring billions of years in the past, signal their own magnificent deaths? Or are they merely beacons for our learning? Every time we chart a new distance, we feel the thrill of discovery layered upon the melancholic weight of deep time. The effort to measure the universe is the human spirit's attempt to anchor itself against the ceaseless flow of light from the past. The light curves from these supernovae provided the first hard evidence that the expansion of the universe was, in fact, accelerating. If that acceleration is caused by dark energy, then the light we see is being stretched by a force we cannot perceive or define. It means that the very medium through which we gain our knowledge is actively working to pull that knowledge further and further away from us. The universe seems to be hiding its secrets not by absence, but by an ever-increasing distance between the event and the observer. The concept of the cosmic horizon dictates that there is a limit to how far back we can ever hope to see. Even in theory, what mysteries lie beyond that horizon, permanently shrouded not by darkness, but by the sheer, unbridgeable span of time elapsed? The horizon represents the ultimate boundary of our collective memory, the point where history dissolves into pure, unknowable potential. We must find peace not in seeing everything, but in understanding the profound implications of what we are forever destined to miss. The light from the sun, which seems immediate, is actually 8 minutes and 20 seconds old by the time it reaches our eyes. If the sun were to vanish instantly, we would live in ignorance of that catastrophic event for more than 8 minutes. This small delay reveals a fundamental lesson. Our perception of security is always a few moments behind the universe's true state. We exist in a perpetual state of historical lag, constantly adjusting our understanding based on echoes arriving from the immediate past. Within our own galaxy, light from the center takes about 26,000 years to reach us, framing the Milky Way's history. When we map the galaxy, we are not drawing a current picture. We are assembling a mosaic of moments from 26 millennia. Imagine the civilizations that might have risen and fallen in the spiral arms during the time that light traveled to reach this observatory. Our sense of place in the galaxy is contingent upon the speed of light, making space and time inseparable components of our reality. If we hypothesize a universe where light traveled infinitely fast, the cosmos would appear static, unchanging, and devoid of deep history. Would the philosophical weight of existence lessen if we could see the present state of every distant object simultaneously? The finite speed is what grants the universe its narrative structure, layering scenes upon scenes in the vast theater of expansion. Without this temporal delay, the universe would become a flat, immediate plane, stripping away the mystery of its profound age. It is the slowness of the messenger that forces us to contemplate the magnitude of the message it carries across the void. Stellar archaeology, the study of ancient light, is thus less about astronomy and more about the patient, careful reading of deep history. What if an advanced entity could manipulate this flow, sending light backward along its own path, effectively witnessing its own creation? Such an action would violate causality as we understand it, turning the orderly progression of events into an inaccessible loop. We are thankful, perhaps subconsciously, for the strict rules of the cosmos, which keep our personal histories safe from retroactive rewriting. The unidirectional flow of light confirms our subjective experience. We are bound to move from memory into the future. If we consider gravitational waves as another form of historical messenger, they travel at the same speed as light. They allow us to witness the mergers of black holes, violent events whose light signatures might take millions of years longer to reach us. We are gaining a richer, multi-sensory history book, reading the universe not just in pictures, but in the very shaking of space-time. Each new messenger, however slow, adds another texture to the tapestry, deepening the complexity of the narrative we are slowly assembling. The light reaching Earth today is intrinsically linked to the moment of its emission, serving as a perfect, untainted record. Could an error in the ancient emission, a slight flicker of instability, be preserved perfectly in the light stream for eons? It suggests that the universe does not forget. Even in its most chaotic moments, every cosmic event leaves an indelible, luminous signature. If we listen closely to the silence between the ancient beams, we might hear the music of a cosmos entirely different from our own. Some theorists propose the possibility of relics from a previous cosmic cycle, light that has already traveled the entire history once before. If that were true, we might be observing not the beginning, but a faint, echoing repetition of a grand, forgotten drama. The thought that our present moment is a mere echo of a previous iteration brings a strange sense of cosmic continuity and belonging. We are not just observers of history. We are participants in an infinite loop, lit by the memory of what has been before. The earliest structures we detect are diffuse and irregular, lacking the clear spiral or elliptical organization we see in mature galaxies. What conditions must have existed for matter to clump together for the first time, forming the seeds of everything that followed? It speaks to the resilience of structure, the innate drive of the cosmos to organize itself out of primordial chaos and pure energy. From the formless potential of the initial light, the universe began the long, patient work of sculpting itself into recognizable shapes. The light from these protogalaxies is stretched so significantly that some signals arrive entirely in the radio spectrum, invisible to the eye. If our instruments were only capable of seeing visible light, we would remain completely ignorant of the universe's true, foundational history. This reliance on specialized tools reminds us how much of reality is hidden just beyond the limits of our native human senses. Our understanding is only as deep as the technology we invent to capture the whispers from the edge of time itself. The observation of ancient light requires a profound stillness in our own world. Even the slightest terrestrial vibration can corrupt the faint signal. Is this why the universe communicates through such slow and arduous light? To test the patience and dedication of any potential observer, I have spent decades in silence, waiting for data packets, learning that the greatest discoveries demand the greatest expenditure of attention. The cosmos rewards not aggression or speed, but a profound, almost meditative stillness in the face of its incomprehensible scale. The light of the earliest stars, population 3 stars, composed almost entirely of hydrogen and helium, has never been directly seen by us. These pioneers of light forged the first heavy elements, the very building blocks of our bodies, and then vanished into history. They died in spectacular fashion so that we might exist. Yet their final, magnificent blaze remains forever out of our visual reach. We are literally made of the ashes of stars, whose light has not yet completed its journey to tell us their story of creation. Stellar archaeology then becomes a philosophical exercise in extrapolating from faint evidence, trusting the physics of light travel. What if the universe is not constantly expanding outward, but is instead slowly settling into the vast memory it has already created? It implies that the future might be less about new creations and more about the slow, steady contemplation of everything that has already happened. Perhaps wisdom is simply the recognition that the most important revelations are those that have been traveling to us for the longest time. The current theory posits that all matter began as a nearly uniform soup of fundamental particles following the Big Bang event. If the initial state was near-perfect uniformity, what microscopic quantum fluctuation first initiated the journey toward structure and complexity? It mirrors the human condition, an infinitesimally small beginning that blossoms into an entire universe of subjective experience and emotion. The great cosmic structure is built upon a nearly imperceptible difference, a tiny imbalance that dictated the destiny of all future light. We analyze the polarization of ancient light, looking for clues about the magnetic fields that governed the very first moments of formation. If these nascent magnetic fields were complex, could they have subtly directed the path of the earliest photons we now observe? Even in its infancy, the universe seemed intent on weaving patterns, suggesting intention in what we often dismiss as random chance. The initial forces were not just about physics. They were the first brushstrokes of an immense, unseen artistry being laid down. The light we capture from distant objects is subject to gravitational blue shift when approaching a massive object, or redshift when receding. If we could find a light source that was perfectly stationary relative to us, its light would remain unchanged by the distortions of time. Such stillness is the rarest state in the dynamic universe, a momentary reprieve from the constant flux of travel and expansion. Perhaps our lives, with their familiar routines, achieve a momentary illusion of this stillness against the backdrop of cosmic change. The Hubble Deep Field image contains over 10,000 galaxies in a single, seemingly empty patch of sky, no larger than a grain of sand held at arm's length. This image is not just a collection of galaxies. It is a window into countless different epochs simultaneously experienced by the observer. To grasp the scale of that picture requires momentarily setting aside our terrestrial concerns and simply allowing the immensity to settle within us. In that small frame of reference lies the entire biography of the cosmos, written in light, waiting for our contemplation. We must account for the slight dimming caused by the energy loss of the photon as it traverses the increasing distance over cosmic timescales. Does the universe expend a measurable amount of its own energy to sustain the journey of every single particle of light we detect? If so, the universe is engaging in a profound act of giving, sacrificing a small part of itself to ensure its history is recorded elsewhere. Knowledge, it seems, is not free. It is purchased with the very substance of the light that carries the information across the dark. The light from the nearest star system, Alpha Centauri, takes a little over 4 years to reach us here on our quiet planet. In those 4 years, entire human political and social landscapes can transform radically, yet the star's appearance remains stubbornly fixed. We are linked to a reality that changes at a geological pace, humbling the frantic tempo of our daily lives and concerns. The stars teach us that continuity is found not in speed, but in the patient persistence of a singular, ancient emission. The light that carries the secrets of the Big Bang is incredibly faint, almost indistinguishable from the thermal noise of our own equipment. How many truly profound, world-altering revelations have we dismissed as mere static, the background hum of an irrelevant universe? The act of filtering the signal from the noise is the essential struggle of science, and perhaps of consciousness itself. To find truth, one must learn to cherish the quietest signals, the ones that require the most focused and dedicated listening. When we observe light, we are observing energy that has traveled for timescales far exceeding the entire existence of our species. If light embodies the past, then the darkness between the stars must represent the unwritten future, the potential yet to be illuminated. This creates a beautiful balance. The visible history balanced against the invisible possibility stretching out before us. The present moment is the razor-thin frontier where memory surrenders to potential, illuminated by the slow, steady arrival of ancient light. The earliest detected galaxies, those observed around redshift Luzzi's 11 Thaler, were chemically simple, dominated by hydrogen and helium elements. What unique conditions fostered the fusion reactions inside those first massive stars that managed to create the first trace of carbon and oxygen? It is a powerful metaphor for learning. The foundational knowledge must be established before the subtle complexities of chemistry can truly begin. Every element essential to our biology was forged in the death throes of light-years distant stellar ancestors that we can only glimpse now. The faintness of the signal requires ever larger collecting areas, immense mirrors designed to capture the maximum possible number of ancient photons. Are we certain that the technology we use to gather this light does not subtly alter the message, favoring certain wavelengths over others? Our instruments are extensions of our curiosity, but they are also limitations, defining the boundaries of what the elder observer can perceive. We must always hold our findings lightly, acknowledging that a better instrument might reveal that our current view is merely a shadow. The concept of the photon as a wave-particle duality confuses our classical understanding of reality. Yet it is the basis of all cosmic visibility. If light acts as both a defined path and a probability wave, how does the universe choose which form to manifest across billions of years? It suggests that certainty is a construct of convenience, a necessary simplification that allows us to navigate a reality built on flux. The universe rarely offers clear statements. It prefers ambiguity, forcing us to draw our own conclusions from the dancing evidence. When a star collapses, the light emitted in its final, furious second travels onward, a terminal broadcast destined for the distant future. If we could intercept that final second of light millions of years before it reached us, what could we learn about finality? It touches upon our deepest human fear, the desire to leave some lasting trace, some final word before the silence takes over completely. The universe, through its light, offers us a form of immortality, an image of our own inevitable end preserved for all future time. Planetary systems orbiting distant stars are only visible through the subtle dimming of their host star's light as they transit. If an alien civilization observed our sun in this manner, what conclusions might they draw about the complex, dynamic world hidden behind it? Our entire existence, our history, our wars, and our poetry is currently reduced to a momentary dip in a single star's luminous output. It is a profound lesson in scale, that significance is relative, and that the grandest events are often hidden in the smallest perturbations. The light we study is a history book with pages printed on the canvas of space, each page illuminated by a different star system. If we could rearrange these pages chronologically, would the unified story make sense? Or would it remain a collection of beautiful fragments? The desire to arrange the fragments, to impose a coherent timeline, is perhaps the most uniquely human impulse we possess. We seek narrative coherence because the universe itself presents it to us, one luminous, time-delayed chapter at a time. The earliest light sources we can resolve are so distant that their very nature challenges the established theories of galaxy formation timelines. What unseen physical laws were in effect during that immediate post-Big Bang era that allowed structures to ignite so quickly in the dark? It's like finding advanced ruins beneath the foundations of a primitive settlement. The timeline of expected development seems to be entirely wrong. The universe does not follow our neatly written textbooks. It reveals its story in brilliant, unexpected flashes across the eons. If we could somehow filter out the light from all but one specific galaxy, our perception of the entire cosmos would narrow dramatically. Would focusing so intently on a single historical thread allow us to discern subtle patterns missed when looking at the whole chaotic panorama? This echoes the scientist's need to isolate variables, to find a quiet corner of reality where the signal is clear enough to be understood. In that focused isolation, we find that even a single beam of ancient light contains the entire biography of creation. The concept of the past being physically present in the light is not poetry. It is a measurable, verifiable phenomenon in astrophysics. If the past is physically here, contained within the photons, where does the concept of gone actually reside within the framework of reality? Perhaps gone is just the state of matter whose light has not yet reached us, patiently waiting in the dark to be seen again. The future is simply the past that has not yet been encoded into the luminous archive we constantly observe. The faintness of extragalactic light forces us to build instruments that mimic the sensitivity of a single, patient eye staring into the void. What other messengers travel across the cosmos at speeds vastly slower than light, carrying information from epochs we cannot even begin to access? Our current knowledge feels so complete, yet it is entirely dependent on the one messenger traveling at the speed of causality. We are like readers of a single, incredibly long scroll, unaware that much of the story exists on slower, unread pages drifting in the dark. The redshift of distant galaxies is the primary evidence for the Hubble expansion, a metric showing the stretching of space between emitting and receiving points. If we could somehow measure the redshift between two nearby stars, would the difference be significant enough to notice over a human lifetime? It puts our terrestrial measurements in perspective. The grand dynamics of the universe operate on scales where human observation is almost frozen in time. We search for change in milliseconds, yet the universe reveals its deepest truths across timescales that render human concepts of urgency meaningless. The light from the early universe, the CMB, is an isotropic bath of energy, meaning it appears virtually the same in every direction we look. If the universe is so vast, why does the oldest light we can see display such surprising uniformity across the entire celestial sphere? This initial harmony feels almost intentional, suggesting that the universe began in a state of unified perfection before fragmenting into complexity. The uniformity of the oldest light whispers of a time when separation did not exist, a cosmic unity that we spend our lives trying to recall. Infrared telescopes are essential because the light from the most distant objects is stretched so far into the red that it becomes infrared. If infrared is the language of the ancient past, what other unseen spectra hold the history of the immediate, present moment? We must learn to see with instruments that perceive the world differently than we do, honoring the unseen pathways of historical information. Our perception of the present is merely what is visible to the naked eye. True reality is woven across the entire spectrum of time. The light reflecting off a distant exoplanet might carry data about the planet's atmospheric composition at the time the light was emitted. Can we truly infer a past chemistry with confidence? Or are we merely projecting our current knowledge onto those distant, ancient skies? It is the quintessential scientific risk, building vast edifices of knowledge upon the fragile, time-delayed foundation of a single photon. Yet, this risk is what drives us forward. The willingness to believe in a history that our eyes alone cannot fully confirm. The light from a supernova in a nearby galaxy arrives with a distinct pattern of element absorption lines, providing a clear elemental inventory. If we could travel to that galaxy and watch the star collapse in real time, how different would our understanding of that elemental inventory become? The distance creates a narrative gap, forcing us to rely on a snapshot instead of the dynamic, continuous process of stellar life and death. We are forever studying the universe's still photographs, attempting to extrapolate the motion and feeling from static, luminous evidence. The brightness of ancient stars also provides clues about the stellar populations that preceded them, forming a genealogical map of luminosity. Could we one day look back so far that we see the light of the very first stars, the mythological beacons of the Dark Age? The anticipation of that discovery is what keeps the observer returning to the scope night after night, seeking that primordial gleam. To witness the first light would be to stand at the threshold of time, looking back at the very moment potential became actualized. The universe is functionally a massive, spherical optical illusion, where every direction we look leads backward in time, never forward. If we could reverse the flow of light, we would watch the universe contract, galaxies rushing back into the singularity of their beginning. Contemplating this collapse gives a powerful sense of trajectory, a final destination toward which all the light that has ever traveled is currently headed. The entire history of the cosmos is a single, grand inhalation, and the light we see is the evidence of that ongoing, inevitable process. The study of light echoes, which bounce off objects in interstellar space, provides localized, high-resolution historical snapshots. Could these echoes reveal things about a supernova event that the direct light missed, like the subtle shadow it cast on a nearby nebula? It is like finding a blurred reflection of an event, an impression left on the surrounding environment long after the main action concluded. Even the secondary information, the shadow, carries its own history, a silent testimony to the primary event's powerful passage. The sheer number of photons required to form a single, clear image demands immense technological accumulation over many years of observation. If we could harness the energy of all the light currently hitting Earth from the entire sky, How much power would that represent? It highlights the fragile, tenuous nature of our perception. We barely gather enough of this ancient energy to form a coherent picture. Our entire field of knowledge is balanced on the capture of infinitesimally small packets of energy that have survived an immense journey. The light spectrum acts as a Rosetta Stone, translating the elemental composition of a star's atmosphere from eons past into chemical terms. If a civilization existed on that star 5 million years ago, would their chemical inventory have been radically different from the remnants we see now? It begs the philosophical question: is intelligence a transient flicker that burns out quickly? Or does it inevitably leave a permanent signature in the light? The light itself becomes the only true historian, an unbiased scribe recording the birth, life, and death of everything across the expanse. We must correct for the effects of Earth's atmosphere, which causes twinkling and slight positional shifts in the incoming ancient light. If we could observe from a stable orbital platform free of air, how much sharper would the image of that primordial epoch become? The human drive to ascend, to escape the atmospheric veil, is fundamentally a drive to touch the past with greater clarity. Our technology is merely an attempt to build a small, silent outpost outside of time, dedicated only to reception. The search for biosignatures in exoplanetary atmospheres relies on detecting specific spectral absorption lines caused by living processes. What signature would a civilization that communicates only through light leave behind in the spectrum of its own suns light years away? It implies that all communication, even across cosmic gulfs, must ultimately resolve into the language of energy and its observable effect. Our silence is matched only by the universe's. Yet in that shared quietude, the light itself becomes the grandest, most articulate dialogue. The light from the center of the Milky Way is perpetually obscured by thick lanes of gas and dust, requiring radio or infrared penetration. If that central region holds the oldest secrets of our galaxy, what is the cost of having them permanently hidden behind a dusty screen? It suggests that the universe conceals its most crucial information not with malice, but simply as an inevitable consequence of cosmic density. We learn that accessibility is not guaranteed. Some histories require us to search beyond the most obvious immediate paths of light. The light that travels from the galactic center is significantly altered by the immense gravitational field of Sagittarius A, our central black hole. Does the bending of this ancient light around the black hole create a warped, distorted memory of that galactic core, unique to our viewpoint? Like a memory viewed through a fog of emotion, the physical truth is skewed by the very gravity of the object at the center. Even the fabric of space-time, shaped by profound density, dictates how we are allowed to remember the universe's deep history. The light that formed the very first structured atoms was the faint radiation released when the universe cooled enough for transparency. If we could see that moment of clarity, would the universe appear as a smooth, glowing surface? Or would the first structures be faintly etched within? It is the ultimate origin story, the moment before shadows and contrast, where everything that would ever exist was held in a uniform radiance. We seek the memory of the beginning, but what we find is a perfect, unblemished state of unity, a concept our divided existence struggles to hold. The rate at which light appears to thin out as we look further suggests an inevitable cosmic fade, an eventual dissipation of historical signals. If the expansion continues to accelerate, Will future astronomers look up and see only the distant echo of the Big Bang, with nothing else visible? This possibility lends a gentle urgency to our current observations, an understanding that the library is slowly locking its oldest books away. We must cherish the light we receive now, for it represents the zenith of our ability to read the universe's luminous biography. Fossils on Earth tell a history measured in millennia. Starlight tells a history measured in the lifespan of galaxies and the universe itself. If a terrestrial historian studied a million-year-old fossil, would they feel the same gap between their life and the subject's existence? The sheer scale of cosmic time forces us to adopt a perspective beyond human empathy, one that must stretch to encompass the concept of eons. Our consciousness serves as the bridge, translating the cold mathematics of light years into the warm, relatable language of experience. The light from a star that exploded 10 billion years ago has traveled through regions containing different dark matter densities along its path. Could variations in the ancient dark matter distribution subtly warp the light's polarization, leaving a subtle clue about that intervening void? Even the invisible scaffolding of the universe leaves its mark on the light, shaping the historical record we attempt to decipher. Everything that exists, seen or unseen, leaves an impression upon the sole messenger capable of traversing the vast, empty distances. The study of light polarization can also reveal the magnetic fields present in the very early universe, far before the first stars ignited. If primordial magnetic fields dictated the orientation of early matter, then fate itself might have been woven into the very structure of energy. This implies that the universe's geometry was decided in the first fraction of a second, a silent, fundamental decree shaping all subsequent light. We look for meaning in complexity, but the grandest truths are often found in the simplest. Most foundational parameters established at the start. The light from our own galaxy, when viewed from beyond it, reveals the spiral arms sweeping majestically across the black background. If we could see the sun's light moving away from us, would the light from our own past be observable from a distant, unknown vantage point? It is a strangely comforting thought that our brief history is being broadcast continuously into the void, an accidental message in a bottle. Perhaps in another billion years, a distant civilization will catch the faint echo of our fleeting, bright moment in cosmic time. The faintness of the signal dictates the need for cooling receivers to near absolute zero, eliminating all thermal noise from the apparatus. If noise is the enemy of history, what does the overwhelming complexity of our own civilization contribute to the noise in our immediate perception? We must quiet our own internal static, the rushing thoughts, the immediate concerns, to make room for the quiet pronouncements of the ancient light. True observation requires a sympathetic stillness, an openness to receive the past without imposing the expectations of the present. The Doppler shift, though usually associated with velocity, is the red shift, blue shift we measure for light traveling through an expanding or contracting space-time. If the universe were to begin contracting, would the ancient light we currently observe start to blue shift back toward its original energy? The vision of a contracting universe, light rushing back toward its source, is a powerful reversal of the narrative we currently inhabit. It reaffirms the cyclical nature of things. Every emission of light carries the potential for its own eventual, luminous return to the center. We can calculate the age of a star by analyzing its light and comparing its current state against the known evolutionary tracks of stellar nurseries? Does the light itself carry an intrinsic signature of the star's intended lifespan, a kind of luminous mortality clock embedded in its spectrum? It resonates with the fleeting nature of human lives. We live out our time, and our passing is simply a change in the light we emit. The light is the record keeper, inscribing every phase of existence, from youthful flare to the long, cool sigh of old age. The faintness of light from extremely high redshift sources suggests that the density of emitting matter was much lower in the early universe. If the universe began diffuse and is now accelerating apart, does that imply that the light we see now is the brightest the cosmos will ever be? This feeling that we are positioned at the peak illumination of cosmic history is both exhilarating and deeply sobering for the observer. We stand in the golden hour of the universe, bathed in the light of a past that is richer than any future it might promise. The light traveling toward us has been continuously filtered, interacting with every field and particle across its immense, lonely route. If we could somehow reverse the journey, could we reconstruct the exact quantum state of the vacuum the photon traversed millions of years ago? The path of a single photon is an unparalleled record of the universe's physical state, a living history written in space-time geometry. To study light is to engage in reverse archaeology, patiently excavating moments from the vast, luminous sediment of deep time. The light from the most distant objects we observe is effectively the light from the universe when it was only a few 100 million years old. Were the observers in those ancient galaxies looking at an even younger universe, seeing light from an even more primordial era than our CMB? It creates an infinite chain of observers, each one peering into a past that is older than any structure they can currently see in their own skies. We are never truly seeing the present. We are only witnessing the history of someone else's present, seen through the lens of time. The coherence of the light wave remains remarkably intact over these vast distances, allowing for sensitive interference measurements. If the universe were truly chaotic, this coherence would have been destroyed instantly. Its persistence hints at an underlying order. This underlying order is the quiet assurance that despite the apparent randomness, there is a foundational grammar governing all interactions. It is the cosmic equivalent of a musical score, where the notes drift far apart but still obey the same harmonic rules. The apparent stability of light propagation allows us to use it as a dependable clock against which all cosmic processes can be timed. But if the speed of light itself varied minutely over cosmic history, all our derived ages and distances would be rendered suspect. The pursuit of certainty in physics often leads us to question the very constants we rely on to make sense of the historical record. We seek the immutable laws, but the light arriving across the eons suggests that even the fundamental rules are subject to the scrutiny of time. The very first light visible to us, the CMB, is composed of photons released when the universe was a hot, opaque plasma. If we could see beyond that epoch, beyond that veil of ionized gas, what would the universe look like when it was truly newborn? The opacity of that early era is a fundamental barrier to our knowledge, an immense wall separating us from the moment of pure beginning. We are forever looking at the moment the universe first became capable of sending a message, not the moment the message itself was conceived. The study of light, when used as a historical probe, demands that we develop an intellectual patience that far surpasses our biological lifespan. What new form of patience will be required When we begin to receive light from objects that are actually 100 billion years old, it requires us to accept that our greatest achievements in understanding will always be rooted in the achievements of the distant, light years past. We are tethered to our ancestors, not just human ones, but the celestial ancestors whose final moments illuminate our current reality. The light of the most distant known object, a galaxy at redshift Ze approx 13.2, is the most ancient light we have managed to capture so far. How many more generations of instruments must pass before we gather the light that started its journey before the first hydrogen atoms had even cooled? Our struggle to reach further back in time mirrors the child trying to grasp a distant, shimmering object just beyond the edge of their reach. The light is the goal, the prize, and the very mechanism by which we attempt to transcend the limitations of our own fleeting moment. When analyzing the light from an old star cluster, we can see all the component stars at different stages of their shared evolution. If a star in that cluster died 1 million years ago, is its light still traveling toward us, existing as a faint, delayed memory of its death? It feels like a quiet empathy for those distant stellar remains, recognizing their final act of blazing brightly for our belated eyes. Every time a star dies, it broadcasts its entire life story across the vacuum, an unintentional but perfect historical record. The light signature confirms the presence of specific metallic elements created during the star's thermonuclear fusion phases long ago. If we could see the star in its prime, would its light reveal a pattern of life and death we could relate to our own brief existence? We look for familiarity in the vastness, seeking parallels in the life cycles of incandescent gas clouds to understand our own transient nature. The universe offers us these comparisons. We are stardust, mourning stardust, bound by the same elemental grammar of birth and decay. When observing the night sky, we are actually seeing a collection of light beams that have taken wildly different travel times to reach us. This means the scene before us is not a simultaneous snapshot, but a composite image assembled from moments separated by millennia. It requires a willful suspension of disbelief to treat this layered reality as a single, coherent panorama existing for our current inspection. The sky is not a picture. It is a living, multi-aged tapestry, constantly reweaving itself with every tick of cosmic time. The faint, spectral lines from early galaxies show evidence of the first generation of element synthesis, heavy elements forming within them. Did the first intelligent beings, if they arose in those ancient systems, gaze upon a sky that looked subtly different? Chemically speaking, their visual world would have been constructed from a harsher, simpler palette, reflecting a younger universe still learning to diversify its light. Our richness of color, our access to complex chemistry, is a debt owed to the massive amount of fiery deaths that preceded our quiet era. The faintness of the background radiation is precisely predicted by the standard model of cosmology, a powerful confirmation of the Big Bang. If this oldest light is our shared foundation, what unifying principle can we derive from an event that precedes all discernible structure? The common origin, imprinted on this ancient light, suggests that despite our vast separation, we are all still fundamentally connected to that initial burst. Separation is a temporary illusion created by time and distance. The universe remains, at its core, a singular, indivisible moment of creation. When we look at the light from a galaxy cluster, we are seeing the light that has traveled through a web of invisible dark matter filaments. Could the warping effects of dark matter subtly alter the light's memory, perhaps introducing phantom images or distorting the true historical narrative? It requires us to trust that the intervening darkness, though unseen, is a predictable architect, not a malicious saboteur of incoming information. The hidden structure of the cosmos dictates the path of the visible history, a testament to the power of the unobserved foundation. Sometimes, a single photon can interact with a planetary atmosphere, scattering its energy in a way that tells us about its composition. If we trace that single photon back across the light years, which of its interactions was the most meaningful event in its long journey? It reminds me of a cherished memory that seems insignificant at the time, yet becomes the defining moment upon later reflection. Significance is assigned not at the moment of experience, but in the slow, careful analysis of its arrival through the corridor of time. The light from neutron star mergers carries ripples of gravitational waves, allowing us to triangulate the exact spatial coordinates of the collision. If the light from that event took 1,000,000 years longer to arrive than the gravitational wave, we would see the aftermath before the event itself. Imagine the cognitive dissonance, watching the peaceful remnant fade while knowing that the cataclysmic origin is still hurtling towards you years later. This highlights the deep fracture between the universal speed limits. History can arrive in different forms, arriving out of temporal sequence. The Doppler shift analysis of the CMB reveals minute temperature fluctuations corresponding to density variations in the early plasma. These tiny temperature differences, measured in microkelvins, represent the very seeds from which all future galaxies and structures would eventually grow. The difference between existence and utter emptiness was defined by a variation smaller than a tremor, a subtle variation in primordial heat. It teaches us that the monumental is always born from the minute, and that the grandest history begins with the smallest of fluctuations. The light traveling from the most distant objects we observe is inherently redshifted by the expansion that occurs during its journey. If we could look back at the moment the light was emitted, that distant galaxy would appear brighter, closer, and physically smaller. We must constantly recalibrate our vision to account for the universe's continuous, active transformation as it ages and expands around the light. The journey of light is not through static space, but through a dynamic, evolving medium that forever alters the message it carries. Telescopes must be designed to capture light across the entire electromagnetic spectrum to piece together a complete historical profile of any celestial body. If an advanced civilization used only X-rays to communicate, we would perceive their entire history as an invisible, meaningless background hum. This forces an intellectual awareness of our own potential blindness. We may be missing entire epochs simply because the light is in the wrong frequency. The scope of the universe's memory is limited only by the sensitivity of the instruments we have not yet managed to conceive. The phenomenon of atmospheric scintillation, or twinkling, is the light scrambling itself due to turbulent air layers above the observatory. If that ancient light, traveling for billions of years, is finally scattered by the air immediately above our heads, what does that say of scale? It is a humbling collision, the immensity of cosmic history brought to a final, chaotic halt by the breath circulating just above our lenses. The last leg of light's journey is often the most erratic, demonstrating that the immediate environment holds sway over the most distant echoes. The time it takes for light to travel from the Earth to the Moon is approximately 128 seconds, a measurable delay in our immediate neighborhood. If we were to conduct a real-time conversation with an astronaut on the Moon, that small delay would force us to speak with measured formality. Even the nearest neighbor demands a conscious adjustment to our pace, showing that the speed of light imposes an unavoidable rhythm on interaction. The universe teaches us that every relationship, no matter how close, exists within a framework of temporal separation that must be respected. The spectral analysis of globular clusters reveals stars that are uniformly old, having formed together at a single point in the galaxy's ancient past. If all the light from that cluster arrives at slightly different times due to distance, how closely can we truly synchronize their shared moment of birth? We are attempting to find the exact second of a collective beginning, a task made complex by the very means we use to observe them. The cluster's age is an average, a necessary compromise between the precision of physics and the inescapable fuzziness of vast, layered history. The discovery of water vapor in the light spectrum of a terrestrial exoplanet suggests a potentially habitable environment in the distant past. If that planet is 10 billion years old, what has happened to its water and its potential life during the 10 billion years since that light left? It is an agonizing thought. We detect a promise of life across the gulf, only to have that promise be entirely erased by the journey itself. The light is not a photograph of the present. It is a beautiful, tragic letter from a past that has already lived out its own conclusion. The scattering of light by interstellar dust causes a phenomenon known as interstellar reddening, distinct from cosmological redshift. If we could remove the effect of this dust, would the light reveal the true spectral signature of the star as it was upon emission? It requires us to mentally peel back layers of intervening material, refining the signal until we reveal the intended message underneath the noise. The universe often hides its most profound truths behind layers of interference, demanding purification before clarity can be achieved. The concept of the cosmic light cone defines the region of space-time from which information can possibly reach an observer at a specific moment. If the universe is infinite, there is a vast amount of history happening right now that will never, under any circumstance, enter our light cone. This is the humbling realization of cosmic isolation, that most of existence is playing out in a theater completely inaccessible to our observation. Our knowledge is strictly limited to the light that has successfully managed the journey across the boundaries set by time and space. The light curves of distant quasars, fluctuating over months, are the result of activity around the supermassive black hole at their core. If the black hole's accretion disk orbits at near light speed, what temporal relationships exist between the fluctuations we observe sequentially? The chaos of that near light speed rotation translates into a subtle, slow-moving drama when observed from our distant, comparatively calm epoch. Even the most violent cosmic engines are forced to yield their secrets slowly, translated by the steady, unforgiving meter of light travel time. The spectrum of a star reveals not only its chemical makeup, but also its surface temperature, dictated by the peak wavelength of its emitted light. If a star's temperature was higher in its youth, then the light from its early life would appear subtly bluer to our receivers. This allows us to chart the internal aging process of distant objects, watching them cool and mellow across billions of years of transmitted color. The color shift is the emotional signature of stellar evolution, a gradual transition from the fiery intensity of youth to the quiet embers of old age. The polarization of ancient light passing near very large structures can give us clues about the orientation of those structures relative to our vantage point. If we could see that ancient structure unimpeded by intervening matter, would its orientation seem natural, or would it suggest an unnatural alignment? It is the observer's constant dilemma. To what degree is the perceived structure an artifact of the medium through which the information traveled? We can only ever see the universe as it appears to us at this specific historical juncture, never as it was in absolute detached reality. The concept of seeing the past is a human abstraction. Physically, we are just capturing photons whose energy and path were determined long ago. If the past is physically present in the light, does the act of observation itself destroy that history, collapsing it into a fixed, measured reality? Is the universe merely a collection of probabilities until our light sensors force a single, tangible, historical configuration into awareness? This idea lends a profound weight to our attention. We are not passive receivers, but active participants in defining what the past actually was. When an ancient galaxy emits light, does it emit a potential history, or a history already fixed by the universe's initial conditions? The light is the immutable messenger, but our interpretation is the variable that gives that message its meaning in the present. The energy spectrum of an aging red giant star shows a distinct peak toward the infrared, indicating a cooler surface temperature than its younger self. If we could watch that star's entire trillion-year lifespan in fast motion, what subtle, non-spectral changes would we observe in its light patterns? The passage of time turns the incandescent youth of a star into the gentle, fading warmth of its senescence. A familiar story. Even in celestial mechanics, we find the human narrative of vigorous youth giving way to contemplative, long-term endurance. The search for technological signatures requires looking for light that is too perfectly monochromatic or unnaturally pulsed. Signs of intelligence. If an advanced civilization uses light for communication, how long would their signal linger in the noise before we develop the acuity to recognize it? We are listening for a message that may have been sent when our own species was still struggling to understand fire, creating a deep temporal mismatch. The true challenge of contact is not distance, but the gap in accumulated history between the sender and the recipient of the light. The light from globular clusters, despite being ancient, has traveled relatively short distances compared to light from the cosmic microwave background. Does the contrast between these two ancient observations, the local and the universal, help us map the structure of the intervening space-time? It is like holding a photograph taken yesterday next to an artifact from the Stone Age. Both are real, but they speak in fundamentally different voices. We must learn to listen to voices of different ages simultaneously, allowing the local present to coexist with the deep, luminous past. The apparent lack of strong magnetic fields in the earliest visible regions suggests a different physical environment during that epoch of initial light. If the early universe lacked the magnetic scaffolding we see today, how did that influence the long-term stability of the light paths? The invisible architecture is fundamental. Without it, the luminous history we rely on would have been scattered into incomprehensible noise. Order, whether chemical or magnetic, is the prerequisite for history to be successfully recorded and relayed across the gulfs of time. The faintness of the observed light requires hours of accumulation time for the detector array, turning minutes of cosmic activity into hours of data processing. If the universe decided to send us a crucial message, but it was too faint to register in our current integration time, would that count as an omission? We must acknowledge that our perception of cosmic history is biased by our current technological threshold for gathering faint, traveling energy. The narrative of the universe is co-authored by its events and the patient ability of the observer to capture the dying embers of light. The atmospheric blurring that causes twinkling also slightly randomizes the arrival time of photons within a single measurement integration. If we could correct for every atmospheric quiver across the centuries, how much closer would our reconstructed image be to the true past? It is an ongoing battle to strip away the immediate, the local, the terrestrial, in a persistent effort to hear the cosmic signal clearly. Every technological refinement is an act of historical purification, clearing the static so the voice of the deep past can be heard again. The light from distant globular clusters is so tightly packed in time that the entire cluster appears to have formed almost simultaneously. What organizational imperative forces hundreds of thousands of stars to ignite and evolve within such a remarkably compressed temporal window? It speaks of moments in time where conditions were so perfect, so finely balanced, that the process of creation was temporarily accelerated. These clusters are monuments to a powerful initial impulse, showing what can be achieved when the universe focuses its intent on a single moment. If an object orbits a supermassive black hole close to the event horizon, its light will be severely time-dilated from our perspective. To an observer falling in, the external universe would rush through its entire future history in a near instantaneous flash of light. The concept of being trapped outside of time while watching all future history unfold in a single, brilliant burst is profoundly alien. The boundary of knowledge, the event horizon, is the ultimate barrier to historical continuity, sealing the light and its message away from us forever. The light emitted by a hydrogen atom is quantized, meaning it occurs only at specific, discrete energy levels that act as a chemical fingerprint. If the laws governing atomic emission were slightly different in the early universe, the light arriving now would present a completely unrecognizable spectrum. The delicate balance of these fundamental constants is what grants us the ability to read this ancient historical document at all. Our ability to understand the past is entirely dependent on the universe having chosen predictable and stable laws for its long transmission. The light from objects receding due to cosmic expansion is stretched, causing a loss of energy that shifts the wavelength toward the red end. If we could see the light emitted before the acceleration began, would it appear sharper, brighter, and less diluted by the ever-stretching space? It highlights the subtle tragedy of our position. We are viewing the light after it has been weakened by the vast, ongoing expansion of everything. The universe is constantly working against the clarity of its own narrative, thinning the ink with every passing moment of its accelerating existence. The observation of ancient solar systems allows us to place constraints on the duration of the habitable epoch in cosmic history. If life requires a star older than a certain age to forge heavy elements, what does the light tell us about the earliest possible emergence of consciousness? The light suggests that the conditions for complex existence were extremely rare and required the spectacular death of previous stellar generations. Our existence, seen through the lens of light, is a beautiful, improbable consequence of cosmic violence performed billions of years ago. In observing the light from binary star systems, we can measure the precise mass of the stars based on their orbital period and separation. If one star in the pair is a white dwarf, its light is the final, dense ember of a star that expanded and died long before we existed. We are seeing a relationship caught in a temporal mismatch, where one partner has already completed its life cycle, while the other continues its slow burn. Binary systems, when viewed across light years, become living metaphors for memory. The presence of one object defined by the echo of another. The angular size of distant galaxies, when corrected for lensing and redshift, allows for a geometric mapping of the universe's expansion history. If the angular size of a galaxy seems larger than expected for its redshift, does that imply the expansion rate was slower in that earlier epoch? These tiny deviations force us to treat the cosmos not as a machine running smoothly, but as an entity whose processes sometimes shift unexpectedly. The history of the universe is not a straight line, but a series of subtle curves and adjustments, written in the varying apparent sizes of its light. The faintness of light from an object near the cosmic horizon pushes our instruments to their absolute limit, requiring longer integration times. What if the most profound secrets of the universe were transmitted in a light too weak for us to ever collect, forever remaining just beyond our grasp? The quest for knowledge always confronts the potential for ultimate failure. The quiet realization that the most important information might be forever lost to dimness. We learn to appreciate the light that does arrive, understanding it as a miraculous victory against the overwhelming forces of diffusion and distance. The light from the sun passes through the Oort cloud, a spherical reservoir of icy bodies, before truly entering our immediate solar neighborhood. If we could see that light interacting with those ancient, distant ice masses, would we gain insight into the primordial material of our own system? Our own solar system carries its own deep history, written in the faint reflections off the cold, dark objects orbiting at its fringes. The past is not only found in the light from far away, it lingers, frozen and silent, in the outskirts of our own local dominion. The light from very young, hot stars is predominantly blue and ultraviolet, indicating high surface temperatures characteristic of early stellar formation. If we were observing the universe through only the UV spectrum, our view of cosmic history would be dominated by the fiery youth of everything. We would perceive a universe of perpetual, energetic ignition, entirely missing the slow, patient cooling that defines its ancient maturity. The full portrait of history requires all colors: the blue intensity of creation, the red decline of old age, and the invisible quiet between them. The study of spectral absorption lines provides a velocity measurement for the source object based on the measured Doppler shift of the characteristic lines. If an object is moving toward us at extreme speed, its light will blue shift so intensely that the past becomes visually compressed into the future. This compression of history into a single, high-energy moment speaks to the disruptive nature of rapid motion against the steady flow of time. Even motion itself alters the memory we receive, twisting the slow narrative of light into a sudden, high-velocity declaration. The light collected by space telescopes must be stored digitally, converted from analog energy flux into discrete bits of information for later analysis. Does this digitization process subtly erase the analog nuances of the original photon's journey, imposing a digital resolution on historical truth? We are forced to digitize the past, accepting that we can only capture a fraction of the continuum that actually traveled across the void. Every piece of astronomical data is an approximation, a best effort to reconstruct a perfect moment using the limited vocabulary of measurement. The light from a quasar is so intense that it can sometimes outshine the entire galaxy containing it, making the host galaxy difficult to resolve. If the galaxy's history is written in its fainter stellar light, are we becoming too distracted by the bright, brief roar of the central engine? It is a metaphor for attention. The urgent and the bright often obscure the quiet, steady background narrative that defines the long-term story. We must deliberately look past the grand spectacle to find the subtle, enduring history etched into the surrounding, quieter light. The light from nearby nebulae is constantly interacting with dust, leading to complex emission and absorption features that map out chemical processes. If the gas clouds are constantly shifting, does the light we see represent a single chemical state or a layered, turbulent mixture of ages? The nebula is a place where the past is being actively rewritten by light, scattering off newly formed matter. A dynamic historical churn. Even in regions of apparent stillness, the light reveals a constant, slow conversation between the ancient energy and the freshly synthesized material. The study of light polarization in the outer reaches of the galaxy reveals the coherence of the local galactic magnetic field structure. If that magnetic field acts as a guide, are the paths of ancient photons subtly channeled along its unseen lines across the vastness? We rely on an invisible cosmic infrastructure to deliver the visible history, a dependence we rarely acknowledge until the signal degrades. The coherence of the whole picture depends not just on the source, but on the fidelity of the invisible pathways the message traversed. The faint glow of the zodiacal light is sunlight scattered by interplanetary dust particles orbiting close to the plane of the ecliptic. This light is practically contemporary, yet it still tells a history, the history of collisions and outgassing events within our own solar system's dust. Even here, in our immediate vicinity, the present is merely the most recent scattering event, the result of ancient cometary debris being swept up. We are never truly free of the past. It is in the dust motes floating near our planet that the history of planetary formation remains visible. The light from Type 2 supernovae provides crucial evidence for the nucleosynthesis processes that create elements heavier than iron in the final collapse. If the star collapses slightly faster or slower, the resulting spectral signature would be altered, changing the historical record of element creation. The creation of gold or uranium is a process dictated by the precise timing of a massive object's final, brilliant implosion. The most valuable elements in our world are simply the fossilized light from distant explosions, delivered to us across unimaginable gulfs. The faintness of the light coming from the very first stars means their spectra are extremely difficult to isolate from the foreground noise of later galaxies. What if the key to understanding the universe's first structures lies not in collecting more light, but in designing a filter to remove all later light? To see the beginning, one must learn to ignore everything that has happened since. A profound lesson in historical detachment. True insight into the past often requires willful ignorance of the present, a deliberate, turning away from the nearer, brighter phenomena. The apparent motion of stars across the night sky over centuries reveals their proper motion, the true velocity relative to the sun. If we could reverse the perceived motion of all stars based on their look-back time, would their current positions align into a single, unified point of origin? The universe tries to show us its center through the geometry of its light. But we are forever observing from a moving, biased location. Our place in the cosmos is defined by a constantly shifting perspective, a necessary complication in reading the fixed history written in the light. The light from distant galaxies is spread across an observable spectrum that is dramatically different from the original emission spectrum. If we could see that light as it was emitted, untouched by expansion, would the resulting galaxy appear larger, more defined, and intensely blue? The act of observation is intrinsically an act of historical interpretation, translating the energetic past into the familiar colors of the present. We are the historians of light, tasked with digitally reconstructing the original manuscript from the faded, stretched-out remnants we receive. The spectral signatures of atmospheric gases on exoplanets are remarkably robust, preserving their distinct patterns regardless of distance traveled. If the atmosphere of a planet 10 billion light-years away contained a gas unknown in our local chemistry, how would we even begin to identify it? Our catalog of the universe's potential chemistry is built upon the limited sample size of our own local environment, a fragile basis. The light travels faithfully, but the interpretation remains profoundly local, bound by the knowledge base available at the moment of reception. The light from gravitationally lensed quasars sometimes arrives on multiple paths, creating distinct, delayed images of the same event. If the path lengths differ by years, we can watch the light from the same cataclysm arrive in staggered installments, like slow-motion drama. This is the closest we come to witnessing time distortion firsthand, a single moment fractured into separate, arriving historical reports. The universe reveals its secrets not as a continuous stream, but as overlapping, delayed echoes bouncing off the structure of space-time itself. The light from a distant galaxy reveals the average age of its star population, inferred from the ratio of red giants to blue main sequence stars. If a massive star death occurred recently in that galaxy, its bright, recent light might still be polluting the ancient signature we are trying to measure. We must constantly disentangle the tapestry of light, separating the loud, immediate deaths from the quiet, enduring history of the average population. The true story of a galaxy is not in its most energetic flash, but in the persistent, even light emitted by its middle-aged stars. The light from Earth, traveling outward at speed, forms an expanding sphere of historical information surrounding our planet. If a civilization were located 100 light-years away, they would currently be seeing us as we appeared 100 years in their past. Our current actions are already history for them, a silent broadcast into the void, defining a past that is no longer our present. We are simultaneously living in the present and broadcasting a history that will only be perceived by others in their distant future. The light from an object moving across our line of sight also exhibits a small transverse Doppler shift, independent of cosmological redshift. If we could perfectly measure this transverse shift, would it allow us to calculate the exact moment in the past when the light was emitted? It suggests that for every observation, there is a hidden layer of information telling us when the event occurred, not just where it occurred. The universe demands a multi-dimensional reading. Spatial location, spectral content, polarization, and the precise temporal signature of its movement. The earliest observable structures are often described as clumpy or filamentary, suggesting gravity was already winning the battle against expansion locally. What caused the initial slight clumping? The necessary imperfection that allowed the universe to eventually transition from fog to clear light. It is the story of all complexity, the first deviation from the norm leading to the rich tapestry of structure we observe today. The entire drama of cosmic history began with a microscopic asymmetry, a slight favoring of one region over another in the initial glow. The light from very close stars can sometimes be completely blocked by the dust in our own galactic plane, a local obscuration. If a planet existed right behind a nearby dust cloud, could its light, only a few years old, be rendered permanently invisible to us? This reminds me of personal history. The most recent and perhaps most relevant moments can be obscured by immediate, local circumstances. The nearby past is often harder to read clearly than the distant past, simply because the noise and interference of the present are so strong. The light from a star that is about to go supernova has been traveling toward us for so long that the actual explosion might have already happened. If the light of the final collapse is still en route, is the star technically still alive in the universe's history, even if it's extinguished now? This is the strange comfort of the distant event. The object's end is guaranteed to arrive in our time, a scheduled appointment with history. The light itself functions as a countdown timer, promising the final chapter of a story that began eons before we learned to look up. The faintness of the light from the cosmic web structures suggests that matter is primarily distributed along immense, low-density filaments separated by voids. If the vast, empty voids are truly empty, they represent a period in history where the universe was nearly uniform, a true return to simplicity. There is a quiet beauty in those voids, representing the moments when the universe was waiting, before the gravity of light gathered things together again. The history of structure is the history of light overcoming distance, constantly fighting the expansive pull toward isolation and featureless calm. The light passing through the gravitational wake of a cluster is bent more strongly than light passing through the intergalactic vacuum. Could the light's deflection angle provide a three-dimensional map of the cluster's mass distribution as it existed billions of years ago? We use the distortion of light to map the unseen matter, turning an interference pattern into a profound historical reconstruction tool. The bending of light is a testament to gravity's long memory, showing how massive structures continuously shape the historical messages traveling past them. The search for techno-signatures involves monitoring light for patterns that show periodicity or complexity inconsistent with natural astrophysical processes. If a civilization used a repeating light pulse for millions of years, how would that continuous signal look when filtered through the noise of cosmic expansion? The very persistence required for such a signal suggests a stability and cultural longevity that dwarfs the entire span of human history. They would have learned the art of timeless communication, sending a message whose intent remains clear across the deepest gulfs of cosmic time. The light from the first quasars indicates that active luminous accretion disks were present very early, challenging models of black hole growth timelines. If supermassive black holes formed so quickly, what was the mechanism that allowed them to feed so furiously in the early, sparse universe? The universe's infancy was far from simple. It was a time of violent, energetic formation, accelerating the growth of its largest structures. The light of those early giants screams of urgency, a short, brilliant burst intended to seed the universe with heavy elements quickly. The light emitted by a planet's night side, reflected toward us, can potentially reveal thermal gradients and atmospheric dynamics without direct illumination. Could the light from a planet's past night side, light that has circled the star and returned, contain unique information about its formative years? It suggests that the history of a world is locked not just in its outward gaze, but in the subtle ways its light bounces back and forth through time. Every photon carries a double history: the source of its origin and the complex journey it took to return to the observer's attention. Perhaps the greatest truth gleaned from ancient light is that nothing is ever truly new. We only witness the rearrangement of long-departed energies. This idea brings a quiet comfort, suggesting that the fundamental experiences of creation and decay are eternal, recurring themes in the cosmic archive. The universe never discards its moments. It merely shifts them, redistributes them, and re-illuminates them in different sequences of light. The spectral lines of molecules like carbon monoxide in the interstellar medium provide data points about the temperature and density of the ancient gas. If the temperature was vastly different in the past, those same molecules would have produced an entirely different, shifted spectral fingerprint. We are reading a temperature gauge set billions of years ago, seeking the ambient warmth of a universe that has since cooled considerably. The light serves as a cosmic thermostat, allowing us to chart the cooling curve of existence from white-hot chaos to the current, persistent twilight. The uniformity of the CMB across the sky suggests that the early universe was in a state of near-perfect thermal equilibrium before structure formed. If thermal equilibrium means no information gradient, was the universe, in that moment, incapable of telling any story at all? The beginning was a moment of pure potential, devoid of the contrasts and conflicts that make any story worth telling. Structure, and therefore history, emerged only when this perfect, blinding unity was briefly, infinitesimally broken. The light from an accretion disk around a white dwarf shows evidence of extreme tidal forces, shearing matter violently from a companion star. If we observe this process over millions of years, would the light reveal the moment when the smaller star finally succumbed entirely to the larger one? The light records the slow, inevitable consumption of one body by another, a visual narrative of gravitational dominance played out over millennia. Even in celestial mechanics, we find the echoes of dependence and loss, where one entity's end provides the fuel for another's continued existence. The light arriving from a galaxy that has just passed through a galactic merger shows signs of disturbed kinematics and chaotic stellar orbits. If we could view the merger in real time, how long would the light signature of that violence persist before the system settled into a new equilibrium? The light shows us the aftermath of a cosmic collision, a period of readjustment where the motions of billions of stars are suddenly re-choreographed. The universe, like the mind, takes time to process a shock. The light reveals the residual turbulence long after the initial impact has occurred. The faint glow of an extremely old, metal-poor star provides a direct spectral link to the conditions shortly after the Big Bang itself. If we could perfectly analyze the light from these primordial stars, would they show any evidence of structure that contradicts the CMB data? These stars are the oldest witnesses we have, the direct descendants of the universe's first luminous moments, demanding our utmost reverence. Their light is the closest we come to hearing the original voice of creation, a pure, unadulterated signal filtered only by the passage of time. The apparent size of distant galaxies diminishes rapidly with redshift, making them appear smaller and less resolved the further back we look in time. If the universe were not expanding, the most distant galaxies would appear much larger, offering a clearer view of their ancient structures. The expansion acts as a veil, gradually softening the edges of the past, making the details of creation more elusive with every passing year. We fight against the forces of space and time, seeking to sharpen the image of the past before the expanding veil renders it completely indistinct. The Doppler shift measurement of a single spectral line can determine the radial velocity component of the light source toward or away from us. If we could measure the transverse velocity component from the light's subtle shift across the field, we would have its full, three-dimensional history of motion. The light carries the entire story of its path. But we must employ sophisticated geometry to coax the full complexity of that journey out of the spectrum. Understanding the past requires more than just receiving the signal. It demands a mastery of the forces that shape the signal's trajectory. The light from the Oort cloud objects is so extraordinarily faint that they are essentially invisible, undetectable against the background glow. If those icy bodies reflect the sun's light, and that light has traveled for years, are we viewing the past light of our own star reflecting off that ice? Even in our backyard, the history of light persists, showing us the sun as it was moments ago, illuminating the boundary of our home. Our local history and the grand cosmic history are governed by the same law. The present is always a construction based on delayed, traveling energy. The light from a distant stellar explosion can temporarily outshine its entire host galaxy, creating a brief, immensely bright historical marker. If the purpose of that light was simply to mark the star's death, why was it made so brilliant, so impossible to ignore across the eons? Perhaps the universe insists on a degree of fanfare for its most significant transitions, ensuring the memory of creation and destruction is robust. The brief, spectacular blaze guarantees that the record of the end will be preserved, shining through the fog of intervening deep time. The light from the first stable atoms, the moment of recombination, is the oldest continuous illumination that permeates all of space. If we could see the universe right before that moment, what would the light look like when everything was locked in a plasma state? It was the moment before sight, the last instant of pure, undifferentiated energy before the universe began to speak in discrete beams. The moment the fog lifted was the moment history began to travel, carrying the secret of the preceding silence outward into the vastness. The precise measurement of the cosmic distance ladder depends on calibrating the light from nearby objects before applying the methods to the farthest reaches. If the light from the nearest step in that ladder is flawed, the entire historical reconstruction of the distant universe becomes suspect. Our understanding of the ancient past rests precariously on the integrity of the most recent and closest light we manage to capture. The scaffolding of history requires a perfect anchoring in the present. Even a slight error in the immediate measurement ripples across eons, The light from a pulsar, precisely beamed across space, offers a clock of extraordinary stability, acting as a fixed point in cosmic timekeeping. If a pulsar's spin rate subtly changed millions of years ago, the light we receive now would show a discontinuity in its rhythm. These rhythmic pulses are like the steady heartbeat of a distant entity, an assurance that some processes maintain their integrity across vast isolation. The light from a stable source allows us to calibrate our own, less stable sense of time against an enduring, luminous metronome. The faint, nearly undetectable light from distant rogue planets, unbound to any star, represents history that is almost entirely cold and dark. What would the light profile of such a world reveal about its composition, given that it has received no recent energetic illumination for billions of years? It speaks of extreme endurance, of worlds defined by their solitude, their history preserved only by the minimal heat of their own internal core. The history of the universe is not just a record of light, but also a record of the deep, cold quiet where light cannot easily reach. The atmosphere of Earth scatters blue light more effectively than red light, which is why the daytime sky appears blue and sunsets appear red. If we viewed a distant Earth-like world from across the galaxy, would its reflected light show a similar blue tint, a universal signature of atmosphere? The light that escapes our world carries a subtle, unintentional signature of our own environment, a fingerprint stamped onto the history we broadcast. Every environment imprints itself upon the light that passes through or reflects from it, making every observation a unique record of that location. The observation of time dilation in GPS satellites, caused by both velocity and gravity, proves that light-based time measurements are constantly being affected. If these minor relativistic effects must be corrected for satellite navigation, how much more significant are the cumulative effects over cosmic light years? We are forced to admit that our concept of constant time is an earthbound convenience. The universe insists on a fluid, location-dependent time. The light reveals that time is not a simple river, but a complex ocean, with eddies and currents dictated by mass and motion everywhere. The light observed from the surface of a neutron star, being subject to immense gravity, shows a distinct gravitational redshift effect on its spectrum. If a civilization existed on a planet orbiting that neutron star, would their concept of time passing be radically different from ours due to the local space-time? Their light would be tired, drained of energy by the effort of escaping that immense gravitational well. Conveying a sense of ancient fatigue, the energy signature of light is a direct indicator of the physical stress endured by the source and the space it traversed to reach us. The light from early universe ionization events, when the first stars ignited, temporarily made the universe opaque again to specific radiation wavelengths. What was the appearance of the cosmos during that brief, opaque period, right after the initial CMB glow faded? But before the first galaxies shone, it was a profound interlude of near darkness, a necessary, silent gestation period between the universe's birth and its first true illumination. The history of light is punctuated by shadows, reminding us that clarity requires time and that structure must be forged in periods of near invisibility. The study of light scattering in dense stellar clusters helps map the path density of matter, revealing where the most ancient stars congregate. If the oldest stars cluster tightly, does that mean the early universe favored dense regions over diffuse ones for the initial formation of matter? It suggests that the seeds of structure were planted in concentrated pockets, like tiny, fiercely burning embers in the vast, cooling expanse. The light testifies that in the beginning, unity was fleeting, and the drive toward congregation was an inevitable, fundamental cosmic behavior. If those early regions favored dense pockets, does the light we see reveal a history of rapid structure formation in small, energetic volumes? The light shows us that the seeds of complexity were planted in concentrated pockets, like tiny, fiercely burning embers in the vast, cooling expanse. The light testifies that in the beginning, unity was fleeting, and the drive toward congregation was an inevitable, fundamental cosmic behavior. The spectral distribution of light from a galaxy cluster undergoing strong lensing confirms the presence of enormous, unseen gravitational mass. If the lensing effect is so pronounced, does that mean the cluster's mass distribution from that era is significantly different from its present configuration? The spectral distribution of light from a galaxy cluster undergoing strong lensing confirms the presence of enormous, unseen gravitational mass. If the lensing effect is so pronounced, does that mean the cluster's mass distribution from that era is significantly different from its present configuration? The bending of light becomes a palpable record of gravitational history, showing us the cosmic structures that dominated that ancient time. We see the universe not as it is, but as it was forced to become by the heavy architects of the past, their influence indelible. The observation of faint galaxies at high redshift requires sophisticated instruments capable of stacking many hours of exposure time to integrate the minimal photons. If we could somehow witness the formation of the first galaxies in real time, what sudden bursts of light would break the preceding cosmological silence? That moment, when diffuse hydrogen first coalesced into luminous stars, must have been the most spectacular transition in the entire history of space-time. It was the universe's true dawn, an awakening moment whose light now reaches us as a faint, almost spiritual glow across the eons. The light emanating from accretion disks around active galactic nuclei is often highly variable, flickering on timescales of days or weeks. If the variation is due to turbulence, does that turbulence represent the past physical conditions, pressure, and density in that region near the black hole? The variability mirrors the chaotic nature of our own short-lived decisions, where rapid changes can define the character of a moment forever. The universe's history is written in both the steady glow of mature systems and the frantic flicker of its most intense, volatile events. When light travels through a region containing a dense star cluster, the probability of photon interaction, absorption, or scattering increases significantly. If a photon is absorbed and re-emitted multiple times, does the resulting light still carry the accurate historical context of its original source? The light's memory becomes layered, a history contaminated by the intervening events of the stellar nursery it had to traverse to reach us. Clarity is a luxury afforded only to the light that passes unimpeded. Otherwise, history becomes a palimpsest of overlapping, confused emissions. The light from the most distant known objects shows a distinct shift in the characteristic temperature fluctuation of the cosmic microwave background. How precisely can we isolate the redshift caused by expansion from the redshift caused by the peculiar motion of the galaxy that emitted the light? The separation of these effects is an attempt to disentangle the universe's overall historical trend from the local, individual movements within that trend. We seek to distinguish the universal law of expansion from the localized stories of galactic motion captured within the ancient light. The light from a white dwarf, being extremely dense, is noticeably redshifted due to the gravitational field warping the energy of the escaping photons. If we could see the light emitted by that white dwarf when it was a normal, large star, would the lack of gravitational redshift show a bluer, younger color? The light shifts color to tell the story of its star's contraction, a visual accounting of the loss of volume and the gain in density over time. The history of a star is written in its color, a gradual dimming that is not merely fading, but a structural warping caused by its own gravity. The search for population 3 stars relies on finding objects so metal-poor that their spectra contain almost no emission lines other than hydrogen and helium. If such a star is found, its light would represent the purest sample of cosmic history, the universe before it began recycling its own elements. To observe such a star is to look at a moment when the universe was simpler, less burdened by the complexity of its own prior creations. This pure light offers a baseline, a quiet moment before the universe learned to write its story using a diverse and heavy chemical vocabulary. The light arriving from the near-future direction of the solar system's movement through the galaxy is slightly blue-shifted due to our proper motion. If we could perfectly cancel out our own motion, would the light from the past appear even older, as if we had stopped moving through time? Our velocity through space is inextricably linked to our experience of time. Movement shapes how much history we are able to perceive. To stand still in space is to experience time in its purest, most historical flow, unfiltered by the biases of our own motion. The spectral analysis of distant galaxy clusters allows us to measure the total amount of baryonic, normal matter present compared to dark matter. If the ratio of normal matter to dark matter was higher in the early universe, would the light from that time show a different pattern of clustering? The light acts as a forensic tool, allowing us to analyze the ratios of ingredients in a cosmic recipe that was executed billions of years ago. We are discovering that the universe's evolution is a story of dark scaffolding supporting a brief, luminous flourish of visible, ephemeral matter. The light from Earth, if observed by an alien over many centuries, would show a distinct, non-random progression of artificial radio and television signals. If that alien were to analyze the light of the 20th century, would they perceive our brief burst of technological noise as our entire historical legacy? Our entire history, our philosophy, our art is compressed into a brief, increasingly faint radio beacon, broadcasting into the darkness. The light carries the undeniable proof of our sentience. Yet it is an echo that will fade, overwhelmed by the sheer, enduring silence of the cosmos. The light from globular clusters shows that the very oldest stars formed from gas clouds that were pristine, composed almost entirely of hydrogen and helium. If we look far enough back, the light tells us there was no carbon, no oxygen, no iron, only the fundamental ingredients created in the immediate aftermath. It underscores the miraculous nature of complex life, that the raw light of the universe first had to cook itself through generations of stellar death. Our existence is predicated on a slow, deliberate alchemy, documented across the cosmos by the light signatures of long-dead star factories. The light from active galactic nuclei travels through the broad line region, a zone of intense radiation where matter orbits very close to the central singularity. If the gas clouds in that region move near light speed, would the light they emit be Doppler boosted to such an extreme that it appears artificially energetic? The physics near a black hole is where the narrative tension is highest, where the rules of time and energy are most violently tested and transformed. The light from that crucible tells a story of extreme physics, of matter compressed and energized to the very edge of possibility before oblivion. The light emitted by a high redshift galaxy has traveled so long that the expansion of space has stretched its wavelength significantly, often into the infrared. If we could hypothetically observe that galaxy as it exists now, it would appear vastly different, closer, more compact, and perhaps much bluer. We are looking at a phantom, a version of that galaxy that has continued its evolution while its past self remains frozen for us in the visible spectrum. The light preserves a moment, but that moment is now decoupled from the continuous reality of the object, making our observation a true historical artifact. The faintness of the light from individual galaxies at the edge of the observable universe means that only the brightest collective emissions are detectable. What if the earliest structures were entirely diffuse, their light too spread out to ever register as a distinct galaxy to our current instruments? The history we are reading might be biased toward the energetic and the massive, potentially missing the quieter, more fundamental forms of early structure. Our history book of the cosmos may be missing entire chapters written in a light too soft or too faint to survive the long, lonely transit. The light emitted by an object is always a record of its state at the moment of emission, entirely independent of subsequent events. If an advanced alien civilization tracked our Earth's light, would they notice a sudden, anomalous spike in artificial emissions around the 20th century? That brief, noisy emission would stand out as the most unique feature of our planet's light history. Our ephemeral scream into the darkness, our entire civilization, our striving, and our art is currently coded into a band of faint, irregular radio waves traveling across the galaxy. The light passing through planetary atmospheres carries spectral signatures of water, methane, and oxygen, which are the historical products of chemical evolution. If we find these same chemical fingerprints on a planet 10 billion light years away, does that imply life's development follows a universal template? The light suggests that the chemical pathway to complexity might be a universal requirement, a necessary step for any history to begin. The universe, it seems, has preferred methods for building awareness, and the light carries the evidence of these preferred ancient recipes. The faintness of the earliest star fields implies that star formation was sporadic and less efficient in the very early universe epochs. If star formation was inefficient, then what subtle difference in the initial conditions prevented the clouds of gas from collapsing more readily? It speaks to the difficulty of beginnings, the immense inertia required to overcome a state of near-perfect, featureless simplicity. The first lights were hard-won victories against the overwhelming tendency toward eternal, cold uniformity, a testament to initial, powerful forces. The light emitted by hydrogen is extremely sharp and distinct, allowing for incredibly precise distance measurements when redshifted accurately. If we could see the hydrogen light before the formation of the first stars, would it be a smooth, featureless glow? Or would the first proto-galaxies show The purity of the hydrogen line represents the universe before complexity, the unedited manuscript before the first stars started writing their own chemical narratives. We seek the original syntax of the cosmos, the basic linguistic components that existed before the grand, expansive prose of galaxies began. The light reflecting off the rings of Saturn, while recent, carries the history of impacts and orbital dynamics within our own system. If a large object collided with Saturn 10 years ago, would that impact event be visible in the reflected light signature right now? The light shows us an ongoing, active history, even in the seemingly placid regions of our own celestial neighborhood. A continuous, slow change. The local past is just as real as the cosmic past. Only the travel time distinguishes one from the other in our perception. The light that has traveled through an active galactic nucleus often shows broad emission lines, caused by the rapid orbital velocity of the gas clouds. If we could watch that gas cloud slow down as the black hole's influence waned, would the light lines gradually narrow over the subsequent millennia? The light would show a slow, reluctant return to stability, a cosmic exhale following a period of intense, high-velocity excitement. Even phenomena occurring at near-light speed leave an extended, time-delayed record of their deceleration and eventual settling into pattern. The light from the earliest galaxies observed by JWST shows chemical compositions suggesting massive, metal-free stars were already forming and dying. If those first stars lived short, violent lives, what would the light signature of their second or third generation of descendants look like? We are tracing the lineage of the elements, watching how the universe learned through stellar consumption and explosion to create complexity. The history of chemistry is the history of light recorded in the ashes of its own brilliant, temporary creators. The search for gravitational lenses requires mapping where light deviates unexpectedly from the predicted straight-line path across the sky. If we could see the light's true, unbent path, would the distant object appear closer or farther away, changing its entire recorded history? Every path the light takes is dictated by the entire intervening history of mass, the dark matter, the clusters, the great filaments. The distortion of light is not an error in observation. It is a fundamental element of the past structure being revealed to us now. The light reflected from the surface of Jupiter shows the chemical signature of its ammonia clouds, revealing its atmospheric composition across time. If Jupiter's composition has remained stable for billions of years, its light acts as a steady, unchanging marker of the solar system's early chemistry. The giant planets are the silent custodians of solar system history, their steady light preserving the initial conditions of our cosmic neighborhood. They are archives of our past, their light offering a slow, reliable confirmation of the environment from which our own brief sentience emerged. The light from the most distant objects is so stretched that the characteristic 21-centimeter hydrogen line is shifted entirely out of the radio spectrum. If the expansion of the universe were to stop, that ancient hydrogen light would suddenly reappear in our radio telescopes, a historical reemergence. The cessation of expansion would feel like the universe finally settling down, the stretching finally done, allowing the oldest whispers to arrive unhindered. It suggests that the past is not gone, but merely wavelength shifted, waiting for the conditions to allow its specific frequency to be perceived. The light from very young stars often exhibits powerful stellar winds, carrying away significant mass and influencing the composition of nearby gas clouds. If we observe a young star that has expelled most of its mass, is the light from that expelled material carrying a different historical signature than the star's core light? The light tells a complex story of stewardship. The stellar ancestor sacrificing its material to seed the next generation with the necessary elements. The brightest light does not always carry the deepest history. Sometimes the faintest emissions from the ejected material tell the richer tale of transformation. The light from distant quasars indicates that black holes were feeding aggressively when the universe was relatively young, contrary to some earlier expectations. If the early universe was less dense, what sustained that rapid growth? Was the initial supply of matter somehow easier to accrete in that epoch? The light shows us a universe in a hurry, racing to build its largest structures before the expansion could pull the necessary components too far apart. The history recorded in the light is one of cosmic tension. The urge to build structure, battling the urge toward infinite, isolating expansion. The light from a star's surface is a direct measure of its effective temperature, assuming a near-perfect blackbody radiator for simplicity. If a star's light is contaminated by an external source, like a nearby supernova remnant, how much of its recorded temperature history is false? We must be vigilant against contamination, recognizing that the history of one object can be subtly overwritten by the dramatic passing of another. The light spectrum is a palimpsest, where the fainter, older histories sometimes underlie the vivid, immediate glow of more recent events. The light reflected from a planet's terminator line, the boundary between day and night, can reveal clues about atmospheric pressure and cloud height. If we could see that terminator line from a planet orbiting a star much older than the Sun, what would the light quality suggest about its evolutionary stage? The light carries the story of that planet's relationship with its star, a visual record of the energy exchange that has defined its billion-year history. Every planet we observe is a silent monument to a specific history of radiation and chemical balance, recorded faithfully in its reflected light. The light from the most distant structures shows a statistically uniform distribution when averaged over very large volumes of space, consistent with isotropy. If the universe is truly isotropic on the largest scales, does that imply a deep, fundamental symmetry dictating the history of all its emissions? The universe displays a profound sense of balance on the grandest scale, a quiet agreement that no single direction holds more historical weight than another. This cosmic impartiality reassures the observer. The history we read is not skewed by our location, but is a universal narrative told in every direction. The faint light of individual, non-luminous objects, like brown dwarfs, can only be detected by the brief shadows they cast across brighter background light. If we relied only on these shadows, our history of the universe would be written entirely in negative space, a record of what is absent. It is a philosophical challenge to find meaning not just in what shines brightly, but in the shape and pattern of the darkness that remains. The history of matter is often revealed not by its own emission, but by the way it subtly influences the light passing by it from another source. The light emitted by an object moving at near the speed of light will appear highly beamed, focused into a narrow cone in its direction of travel. If a hypothetical civilization used such high-velocity emission beams for communication, how much more intensely concentrated would their historical message be? The universe rewards efficiency. The fastest messengers are the ones that focus their energy, ensuring their historical data is received with minimal loss. The light of the past tells us that maximum impact often comes from maximum focus, a concentrated effort that pierces the surrounding static. The light from planetary nebulae reveals the final stages of low to intermediate mass stars, where the outer layers are gently expelled into space. Does the light carry any record of the internal struggles of the star during its transition, or only the final, diffuse glow of its expelled shell? The nebula is the quiet epilogue to a long life, a soft fading that contrasts sharply with the violent death of its more massive cousins. The history of light shows that endings are not always catastrophic. Sometimes they are slow releases, an eventual return to the collective reservoir. The faintness of the extragalactic background light sets the ultimate constraint on how far we can peer into the universe's history before it becomes truly invisible. If dark energy continues to accelerate expansion, will the light from galaxies beyond a certain distance become so redshifted that it simply disappears from detection? This is the tragedy of the accelerating cosmos. The potential light of future discoveries is already being stretched beyond the reach of our current and future senses. The universe is actively unseeing itself, retreating into a future where its history, the light we study, will become forever inaccessible. The light from the cosmic voids, the emptiest regions of space, is the purest measure of the CMB, as there are almost no intervening sources to distort it. If the voids represent the historical default state of the universe, what does the light gathered from these quiet regions truly tell us about the beginning? The void light whispers of simplicity, of the time before matter had found its paths, a near return to the initial, featureless expanse in the universe's quietest corners. The light reveals the most ancient truth. That profound stillness underlies all subsequent moments of explosive history. The apparent color of a distant galaxy is heavily dependent on the intervening dust, which preferentially absorbs and scatters shorter blue wavelengths. If we could somehow see the galaxy with its intervening dust miraculously erased, would the galaxy appear vividly blue, suggesting intense, young star formation? The light arriving now is the seasoned traveler, slightly tired and reddened by its journey, while the true, vibrant youth of the source remains hidden. We must always account for the journey's toll, understanding that the light's current hue is a mixture of the source's age and the distance traveled. The light reaching us from the Laniakea supercluster, our current home structure, has been influenced by the gravitational pull of that entire immense collection. If we could observe our local cluster from a reference frame outside its gravitational influence, would the light paths appear straighter, revealing a different history? Our local history is constantly being shaped by the unseen pull of our neighbors, a dynamic that subtly bends the light traveling past us. The path of light, even on local scales, reveals that we exist within a complex, moving tapestry woven by gravity and time. The faint infrared glow from the early universe is now being mapped to trace the distribution of neutral hydrogen gas before the first stars ignited. If we could see that dark hydrogen distribution clearly, would it show a structure far more organized than the structure formed by the light of the first stars? The structure exists in the dark matter long before the light shines, The blueprint precedes the illumination, written in the absence of photons. The history we read in light is merely the visible consequence of a much deeper, much older structure written in the invisible scaffolding. The light from a type Ia supernova, though appearing identical, has subtle differences in its rise time related to the mass of the progenitor white dwarf. If we could watch that explosion unfold, frame by frame, across 1 billion years, would we see the subtle variance in the explosion mechanism? Each supernova is a unique event, yet the light that reaches us is an average, forcing us to rely on statistical patterns to discern individuality. The grandeur of the cosmos is often understood only through the patient aggregation of countless singular, time-delayed moments of violence. The light from the center of the oldest known galaxy cluster appears heavily sheared and smeared due to the extreme gravitational field of the entire structure. If we could remove the gravitational distortion, would the center of that cluster reveal an ancient, tightly packed collection of primordial stellar remnants? The light has been warped by the very density it is trying to describe, an inherent paradox in mapping gravitational history. The structure of space-time, imprinted on the light, is the truest record of the mass that has accumulated across the history of that galaxy cluster. The search for the first stars requires instruments sensitive enough to detect the faint signature of a single, massive star against a universe full of dimmer, later sources. If we manage to perfectly isolate the light of that very first star, what universal principle would its existence confirm or shatter about the beginning? The culmination of this long observational effort is to glimpse the single moment when the universe began to organize its own memory through light. This quest defines us. The desire to read the first line of the cosmic book, to know the Genesis event through its most enduring messenger. But what if the universe has a secret mechanism, a way to communicate across time that bypasses the relentless speed limit of the photon entirely? We are constrained by the speed of light, yet our greatest discoveries, like gravitational waves, show that space itself is dynamic and responsive. If space-time can ripple, carrying news faster than light in certain theoretical models, then our entire historical timeline might be built on an incomplete assumption. The thought that the deepest past might not be locked behind that light barrier introduces a profound, almost frightening possibility into our contemplation. If time is flexible enough to bend light, perhaps it is also flexible enough to allow the most ancient truths to arrive in a form we have yet to recognize. The principle is that no information can travel faster than cz in our local reference frame, an established constant of relativity that holds for light. However, the expansion of space itself is not limited by CE, creating distances where the light emitted now will never reach us. This is the true historical severing, the realization that vast portions of the universe's history are being permanently locked away by accelerating expansion offers a stark lesson in impermanence. The light we seek is not just history. It is a precious, non-renewable resource, fading as the universe tears its own pages out of our reach. If we focus on what we can measure, the light that has arrived, we must treat every photon as a unique, irreplaceable historical witness. What if the universe is preparing another messenger, one slower than light but more durable, carrying the history across the widening chasm of dark energy? We must listen for the slow messages, the ones that defy the rapid tempo of light, trusting that persistence holds its own form of profound information. The true depth of history might be measured not by speed, but by endurance. The ability of a message to survive the slow, relentless erosion of time and space. The faint light from the earliest galaxies allows us to trace the history of ionization. The epoch when the universe cleared its smoky fog. If that ionization process took hundreds of millions of years, what kind of subtle, flickering light characterized the transitional phase between opaque and transparent? It suggests an epoch of profound uncertainty, a long, drawn-out dawn where visibility was uncertain and history was written in shifting shades of gray. Even the universe has stages of struggle, long periods where the clarity of its own narrative is obscured by the very material from which it is forming. The Doppler measurements of the cosmic microwave background reveal a slight dipole anisotropy, caused by the Earth's motion relative to that ancient background. If we could eliminate the effect of our movement relative to the CMB, would we see a more perfectly uniform map of the universe's true beginning? Our every measurement of the past is tainted by our motion in the present, forcing us to account for our own temporary place in the river of time. To truly see the absolute past, one must first stand perfectly still, an impossible requirement in a universe that is constantly expanding and moving. The light from binary pulsars, orbiting closely, experiences significant time dilation due to their extreme gravitational potential and orbital velocities. If the orbit decays over millions of years, the light pulses arriving now should show a consistent, measurable shortening of the period, confirming energy loss. The light records this subtle, inevitable decay, charting the slow death of orbital energy as it bleeds away across the vast reaches of space. Even the tightest, most energetic systems are subject to loss. Their history, an elegant, measurable drain on the energy that illuminates them. The light collected from the early universe is often characterized by a lack of sharp features, as the universe was too hot and dense for complex atoms to form. If the universe had cooled slightly faster, would the first light have contained the spectral signature of neutral hydrogen, a true visual birth certificate? The difference between the plasma fog and the first clear light represents a critical inflection point in the universe's ability to record its own history. That epoch of clarity, the moment the light broke free, is the historical event that made all subsequent observation and memory possible. The chemical composition of distant star clusters, inferred from light analysis, confirms that the heavier elements required multiple generations of stellar death cycles. If the light from a very old cluster shows traces of heavy elements, how many stellar life cycles must have elapsed between the Big Bang and that light's emission? We are looking at a legacy built on failure and rebirth, recognizing that our own existence relies on countless unobserved, violent stellar ends. The history of matter is a story of continuous recycling, where the light simply tracks the progress of this slow, energetic transformation. The redshift, $C value for a distant object, is a direct proxy for its look-back time, defining how far into the past we are observing. If we could find an object with an infinitely high redshift, would its light arrive from a point before the universe had time to develop a recognizable structure? The pursuit of infinite redshift is the quest to find the ultimate historical limit, the point where the concept of light as we know it ceases to apply. The edge of our observable history is not a wall of darkness, but a theoretical point where the physics of light itself breaks down into pure energy. The faint signals detected by radio telescopes, even terrestrial ones, are often contaminated by human-made interference, requiring careful filtering. If our own recent light pollution reaches distant stars, how much of the ancient cosmic history we observe is subtly tainted by our own contemporary noise? We risk becoming the very interference we seek to eliminate, blurring the clarity of the past with the immediate output of our present activity. The silence we crave in the cosmos must first be achieved within ourselves, quieting our own emissions before we can hear the faintest echoes. The gravitational redshift observed on the light escaping the surface of a white dwarf is a direct confirmation of Einstein's general relativity theory. If that light's energy loss is precisely measured, does it give us a historical snapshot of the star's mass at the moment of emission? The light is the ultimate bookkeeper, recording every physical toll exacted by the immense gravity of the dense stellar remnant across its entire lifetime. We learn that even the most basic particle of energy carries a historical ledger of the forces it encountered on its lonely, luminous path. The light from the universe's earliest known structures suggests that these proto-galaxies were surprisingly luminous for their young age. If they were so bright so early, what mechanism allowed for the rapid formation of the massive stars required to ignite that universe so swiftly? The light whispers of an initial burst of intense activity, a universe that matured rapidly in its foundational, energetic stages. The historical record suggests that the greatest creativity in the cosmos often occurs during the most turbulent, unstable periods of its youth. But consider this: what if the light we receive from the most distant objects is not a record of their history, but a signal sent to us? The interpretation of light as purely historical data assumes a passive source, an emission simply traveling across empty, indifferent space. What if the patterns in the CMB fluctuations or the precise redshift values are not echoes, but intentional markers placed along the path for future receivers? The transition from passive history to active communication fundamentally alters our relationship with the light. It becomes a dialogue, not a monologue. If the universe is broadcasting a curated history, then our interpretation shifts from mere detection to the profound act of deciphering a deliberate message. This hypothesis requires that the underlying physical constants themselves are stable enough across billions of years to serve as reliable communication channels. If this is true, then the redshift is not merely the effect of expansion, but a coded marker indicating the temporal separation between the sender and us. The light ceases to be just a physical phenomenon and becomes, instead, a testament to a vast, patient, and persistent consciousness existing across all of time. Our historical journey through light is revealed to be a carefully managed historical tour, curated by forces that understand the dimension of time intimately. The light from the most distant galaxies confirms that the fundamental atomic transitions observed locally also governed the universe when it was young. If the atomic laws were different back then, the light arriving now would be nonsensical. Yet we find consistent signatures of hydrogen and helium. This consistency is the bedrock of belief that the universe speaks the same chemical language across all epochs, ensuring intelligibility. The fidelity of the atomic signal across eons is the universe's greatest promise, that its history can, in principle, be read by any sufficiently patient mind. The light from objects near the cosmic horizon is so faint that it merges into a continuous, near-uniform background, glow across the sky. If that uniformity is the maximum historical depth possible, what does it imply about the first few moments of the universe before any structure formed? It suggests the beginning was simple, a soft, glowing canvas upon which all subsequent complexity would eventually be painted by the light of stars. The history is a gradual darkening. The transition from the blinding simplicity of the beginning to the nuanced shadows of the present. The light reaching us from a nearby globular cluster shows an age estimate of over 12 billion years, nearly as old as the universe itself. If these stars formed so early, what was the mechanism that allowed them to survive the subsequent high-energy, chaotic processes of the early galactic center? They are the quiet survivors, the ancient witnesses who have maintained their steady light while the universe raged and transformed around them. Their enduring light proves that stability can emerge even from the most violent origins, a hard-won peace preserved through time. The light from the sun, when entering a dense medium like glass, slows down significantly, demonstrating that the speed of light is not always c. If light slows down in matter, does that mean that the history we read from a distant galaxy cluster is slightly older than the time calculated using only $? The path is never a straight line, nor is the passage of time ever constant. These subtle deviations are the complex footnotes to cosmic history. We must account for every ripple, every slowing, every bend, for these are the physical imprints left by the mass that has structured the past. The light emitted by an object receding faster than the current expansion rate will eventually be redshifted so far that it becomes undetectable. If that light is destined never to reach us, is the history of that object permanently erased from our potential awareness of the cosmos? This is the great cosmic forgetting, where distance and expansion conspire to erase the historical record of entire galaxies from our sphere of influence. The light we receive is therefore a privileged subset of history, a record curated by the boundary conditions of the universe's present configuration. The light from the Andromeda galaxy, due to its slight motion toward the Milky Way, exhibits a small blue shift in its spectral lines. If the light is blue shifted, does that imply that we are seeing the history of Andromeda slightly later than the history of a galaxy receding at the average rate? Our immediate galactic neighborhood offers a slight reprieve from the universal tide, showing us a slightly less aged version of galactic history, even within our cosmic bubble. History flows at slightly different rates, a localized variation in the great universal tempo set by the speed of light. The light reflected from Kuiper Belt objects is extremely faint, requiring the longest integration times to discern even their basic orbital parameters. If these distant icy bodies harbor any volatile chemistry, their light signature might preserve the thermal history of the solar system's formation era. They are frozen time capsules, holding on to the chemical whispers of the past when the sun was still surrounded by its chaotic, dusty disk. The faintness of their light forces us to acknowledge that the most ancient, formative moments often leave the most subtle, easily missed evidence. The light spectrum of a carbon star shows an overabundance of carbon compared to oxygen, indicating a specific stage in late-stage stellar evolution. If we could watch that star slowly cook itself over eons, would the light show a gradual enrichment of carbon or a sudden, dramatic event? The light is a record of transformation, capturing the slow chemical migration within the star before its final dispersal into the galactic medium. The history of a star is written not just in its brightness, but in the subtle, shifting proportions of its chemical ingredients revealed in the spectrum. The light from the earliest gravitational wave events, combined with electromagnetic counterparts, allows for an independent calibration of the Hubble constant. If the Hubble constant, derived from light history, differs significantly from the constant derived from the present-day motion of local galaxies, which history is correct? The discrepancy reveals that the universe's expansion rate is not fixed. It is a historical variable, changing over the eons that the light has traveled. The light across time confirms that the cosmos is dynamic, that its own rules of progression are not static, but evolve as it ages. The light from the quasar 3C 273 was the first recognized identification of a quasar, demonstrating extreme luminosity across billions of light years. If that quasar is still active, how has the light from that core activity changed over the thousands of years since its initial discovery by our instruments? Our own history of observation is short, yet even within our limited time frame, the light reveals that these massive engines eventually ebb and flow. The light tells us that even the universe's most spectacular phenomena are ultimately transient, subject to the same finite lifespan as a single star. The light polarization from interstellar dust grains reveals that these grains tend to align themselves perpendicular to the galactic magnetic field lines. If we could see the light from a time before the galactic magnetic field was fully established, would the dust grains appear randomly oriented, showing no alignment? The magnetic field is an invisible architect that shapes the light paths, an imposed order on the trajectory of historical messengers. The alignment of the dust is the imprint of a force that existed long ago, subtly directing the flow of information right up to our present vantage point. The light emitted by atoms in a strong magnetic field experiences the Zeeman effect, splitting spectral lines into multiple components. If the field strength of a neutron star's surface is inferred from the splitting of its light, does that tell us about the star's early magnetic history? The light holds the record of the star's magnetic temperament, the unseen force field that governed its interaction with its plasma environment over ages. The story of a star is not just in its light output, but in the complex, invisible fields that shape and stress that light as it finally escapes. The light from the leading and trailing edges of a rapidly rotating object will exhibit a slight Doppler shift difference due to the varying velocity component. If we could resolve these two sides separately, we would effectively be viewing the same object at two slightly different points in its own past rotation. The object's light carries a built-in time lapse, showing us different temporal slices of its rotation as the two light paths arrive at our instruments. Every rotating source of light is a subtle time machine, presenting different moments of its own life simultaneously, separated only by the speed of the light itself. The light from the most distant known objects has been traveling for over 13.5 billion years, placing them firmly in the early universe. If the universe were only half as old, how differently structured would the light from that era appear? Would the galaxies be more compact? Our perception of cosmic structure is intrinsically tied to the total accumulated light travel time we can currently access. It sets the scale of our history. The depth of the past is defined by the distance the photon has managed to bridge, a measure of sheer, relentless travel. The light reflecting off our moon shows us the moon as it appeared several seconds ago, a near-present record of its surface condition. If the moon were suddenly covered in a layer of dust, How many hours would pass before the light reflecting off that dust reached our instruments? Even this nearest history demands patience. The light must still make its round trip, proving that the speed limit applies to all messengers. The universe compels us to learn slowness, even in the immediate vicinity of our own celestial home, demanding respect for the fundamental constant. The light intensity measured from a galaxy decreases with the square of the distance, a simple inverse square law that dictates visibility. If we could somehow gather all the light from a distant galaxy that has passed Earth over 1,000 years, how much more detail would we see? The true history is not a snapshot, but a slow accumulation, requiring the patience to collect the faint remnants across decades of dedicated observation. Understanding the past is an act of accretion, gathering the diffuse evidence until the faint whispers coalesce into a recognizable historical form. The light from a Type II supernova is so bright it can momentarily outshine the entire host galaxy, providing a single, intense historical spike. If that single photon carries the news of a star's death, what else? What chemical, magnetic, or temporal information did it manage to record during its long transit? The dying star broadcasts its entire past in that final, brilliant flash, ensuring its legacy is imprinted across the light years it traverses. Destruction, in the cosmic view, is merely a mechanism for ensuring that the history of creation is amplified and broadcast to the future. The polarization of light that has passed through the accretion disk of a black hole shows how warped and twisted the local space-time geometry is. If the black hole is actively feeding, does the light reveal a cyclical pattern in the warping, suggesting a predictable history of gravitational stress? The light orbiting so close to oblivion tells a history defined by the most extreme forces, a record of near annihilation preserved by a hair's breadth. The edge of the abyss is where the story is most intensely written. It is the boundary where time and space are most dramatically fractured. The light from the earliest detected galaxies confirms that the epoch of Ryanization was complex, with pockets of transparency forming before a complete clearing. If we could map those pockets of early clarity, would we see a history where structure emerged unevenly, favoring the paths light could already travel? The universe did not clear all at once. It opened small, tentative windows to the outside, allowing history to seep in little by little. The slow opening of the first visual portals is a metaphor for all learning, a gradual transition from a state of ignorance to partial, hard-won understanding. The redshift of the most distant observable light sets a physical limit on how far back we can trace the history of the universe's expansion rate. If we could look back to the time when the universe was accelerating slower, would the light from that era appear less redshifted and closer? The light carries the history of the expansion rate itself. We read not just what happened, but how quickly the universe was evolving at that time. The light is the most honest historian, showing us that the narrative speed of the cosmos is a key variable in its overall plot. The light emitted by stars within the Milky Way's halo is generally older and more metal-poor than the light from stars within the galactic disk. If we could filter out all the light from the disk, what would the halo's steady, ancient glow tell us about the initial conditions of our galaxy's formation? The halo is the galaxy's memory, the ancient, faithful light that watched the disk form and mature around it, a quiet, eternal sentinel The history of our home is written in layers. The outer shell containing the oldest, most fundamental memories, encased by the brighter, younger disk. The Doppler effect, causing redshift, is entirely dependent on the relative motion between the source and the observer along the line of sight. If we could find a distant galaxy moving toward us at exactly the speed required to cancel out the Hubble expansion, what would its light look like? Its light would be fixed in time, offering a snapshot of its current reality, disconnected from the universal expansion, a truly timeless image. Such an object would be a rare anomaly, existing outside the primary narrative of expansion and contraction, a fixed point in the flow of history. The light from exoplanets in the habitable zone is crucial, as it carries the spectral imprint of a chemistry potentially capable of supporting life. If that light shows complex organic molecules, does that imply that the transition from simple light to self-replicating chemistry is a universal law? The light suggests that the conditions for consciousness are not unique to Earth, but are a recurring theme woven into the fabric of cosmic history. The universe seems predisposed to build observers. The light records the repeated scattered attempts to transition from raw energy to self-awareness. The light from a galactic halo is composed primarily of ancient, low-mass, metal-poor stars, remnants of the galaxy's earliest formation period. If we focus only on the halo light, are we seeing the most honest representation of the galaxy's beginning, unpolluted by later, brighter stellar births? The halo offers the quiet memory of the foundation, the slow, deliberate architecture that supported the more flamboyant, energetic history of the disk. We find that the most profound history is often written in the faintest light, in the stars that have quietly endured the longest passages of time. The light absorption by intergalactic gas clouds, known as the Lyman Alpha Forest, provides a detailed map of the hydrogen distribution in the early universe. If the forest is denser in certain directions, does that imply that the early universe had large-scale structures that channeled the first light beams? The universe's earliest structure is revealed in the gaps of its own light, a history mapped by where the photons failed to pass through unimpeded. Understanding the past requires us to study the obstacles as much as the sources, for the impediments themselves carry the story of the intervening ages. The light from a Type Ia supernova, used as a standard candle, has a consistent decay rate that allows for precise look-back time calculation. If the underlying physics of white dwarf explosion changes over cosmic history due to varying metal content, how does that affect our distance measurements? If the universe sends us a message rather than just an echo, then every observation becomes an act of receiving intent rather than just passively viewing history. This reframes our entire role. We are not just students of the dead past, but intended recipients in a dialogue that spans all of space-time. The light from a distant star cluster shows a smooth progression of ages, consistent with a single, coeval formation event in the galactic halo. If that formation was intentional, what message was being encoded in the initial conditions that resulted in that specific distribution of stellar ages? It implies a vast, almost unimaginable foresight, where the entire 12 billion year life of a stellar population was deliberately sequenced for our future benefit. The history we study is not a chronicle of accident, but a carefully constructed set of reference points designed to guide a future intelligence. The light spectrum of a massive, short-lived O-type star burns out quickly, its entire history spanning only a few million years. If such a star is signaling us, its message must be incredibly dense, conveying its entire history in a brief, spectacular burst of energetic light. It is the universe's equivalent of a profound, concise poem, a massive expenditure of energy to convey a single, vital piece of information. The brief, brilliant signals are the most potent forms of communication, sacrificing longevity for immediate, undeniable impact across the light years. The light detected from an exoplanet's atmosphere during transit is filtered through the thin sliver of atmosphere silhouetted against the star. If we see water vapor, is that an intentional marker placed in the spectrum, or simply the natural result of that planet's atmospheric physics playing out? The search for water becomes the search for agreement, confirmation that the universal laws governing chemistry also apply to the distant, unseen worlds. The light confirms that the conditions for our own life are reproducible, suggesting that our existence is part of a larger, universal theme. The cosmic dawn began when the first stellar light pierced the fog of neutral hydrogen, allowing photons to stream freely across the cosmos. What was the total duration of that opaque era? And what was the nature of the universe during that time when light could not travel unimpeded? That dark period was the universe's gestation, a necessary phase of internal development before it could begin to speak its story outward. The history of light is the history of emergence, the slow, arduous process of energy achieving the freedom to travel and inform. The analysis of the light curve from a distant supernova reveals whether the explosion was driven by standard thermonuclear fusion or core collapse. If we see a supernova that contradicts both known models, does that imply a third, unknown pathway for stellar death? A historical possibility we missed. Each deviation from expectation forces us to reconsider the entire historical timeline of stellar evolution, pushing the boundaries of what we thought was possible. The light consistently shows that the universe is more inventive in its processes than our current theories allow, always holding a few surprises in reserve. The faint, residual light from ancient tidal disruption events, stars shredded by intermediate mass black holes, is exceptionally difficult to isolate. If these intermediate black holes are the building blocks of the supermassive ones, does the light from their ancient feeding reveal the secret of their growth? We are tracing the genealogy of galactic cores, watching the small ones merge and grow, their light combining into the massive beacons we see now. The history of gravity is written in the cumulative light of these mergers, a narrative of constant aggregation leading to increasing central dominance. The light reflected from the surface of a terrestrial exoplanet can indicate the presence of liquid water vapor through specific absorption bands in the infrared. If that water vapor signature is faint, does it suggest the planet is currently entering a drier, less habitable phase of its long, evolutionary history? The light serves as a weather report from epochs past, showing us the climate of a world defined by its star's energy output across the ages. Every planet broadcasts its biography through the light it reflects, detailing the slow, inevitable environmental changes driven by cosmic time. The light arriving from the most distant, gravitationally lensed arcs confirms the existence of dark matter concentrations acting as massive cosmological mirrors. If dark matter is responsible for bending the light so severely, what would the universe look like if it had formed with only half that mass density? The universe we observe is fundamentally shaped by the invisible scaffolding, Without it, the luminous history would be entirely different. Structureless, the light reveals that the visible story is only possible because of the persistent, organizing influence of the unseen components that preceded it. The spectrum of reflected light from a distant object is crucial for determining its surface albedo, how much of the incident light it reflects versus absorbs. If the albedo has changed significantly over time due to atmospheric buildup, how can we correct the current light reading to find the true ancient state? We are engaged in constant historical forensics, trying to clean up the data to see the object as it was, before the intervening years altered its appearance. The light that travels the farthest has undergone the most transformations, making the most ancient observations the hardest to trust implicitly. The light from binary systems, where one object is a black hole, provides precise constraints on the minimum mass of the unseen companion. If the visible star's light wobbles slightly due to the unseen companion's gravity, does that wobble reveal the mass ratio of the pair across time? The visible partner acts as a pointer, tracing the ghostly path of the invisible one across the dark fabric of space-time for us to chart. The universe's hidden history is often revealed not by direct light, but by the subtle, persistent effect the hidden mass has on the visible light traveling nearby. The light intensity from a distant star cluster drops off sharply at wavelengths corresponding to the absorption by large molecules in the foreground dust. If we could observe that cluster from a vantage point outside the dust lanes, would the light reveal a much higher density of stars than currently estimated? Our maps of the galaxy's population are intrinsically incomplete, obscured by veils of dust that have accumulated over countless eons of stellar life. The history of the galaxy is layered. The brightest, most recent light shines through, while the ancient foundations remain stubbornly hidden behind the dust. The light from newly discovered exoplanets in the galactic bulge is heavily affected by the high density of stars and the strong gravitational environment. If planetary formation is difficult in such a dynamic, high-gravity environment, what does the presence of their light tell us about planetary resilience? These worlds are survivors, their light suggesting a capacity to hold on to their form despite the crushing, chaotic history of their galactic core. The history of planetary existence is one of persistence, a quiet resistance against the forces that seek to tear organized matter back into elemental dust. The light emitted from the surface of gas giants shows complex, chaotic weather patterns, but these patterns repeat on discernible, long-term cycles. If we look far enough back in the light, would we see the initial conditions that set the tempo for those long-term atmospheric cycles? The great storms of Jupiter are etched in light across millennia, a visible record of how initial conditions set the stage for the long duration. The universe favors patterns, and the light confirms that even dynamic chaos eventually settles into recurring, predictable rhythms over vast stretches of time. The light emitted by molecular clouds indicates the presence of complex organic molecules, hinting at the chemical precursors to life existing naturally. If these molecules are common, does that mean the universe is primed for life, and that the appearance of life is an inevitable outcome of light-driven chemistry? The light suggests that the ingredients for consciousness are not rare accidents, but predictable outcomes of the universe cooling down and organizing its emissions. The history of the cosmos is a slow process of chemistry achieving complexity, a journey where light illuminates the path towards self-recognition. The light from the largest galaxy clusters shows a slight depression in the CMB temperature in the direction of the cluster, known as the kinematic Sunyaev-Zeldovich effect. Does this slight cooling effect mean that the massive structure is absorbing energy from the oldest light as it passes through the cluster's hot gas? The cluster acts as a massive cosmic sponge, subtly draining the energy from the universe's earliest moments as it collects its own mass over time. The great structures of the universe are not just collectors of matter, they are historical sinks, subtly altering the light of the background history they dominate. The precise timing of binary pulsar light pulses confirmed key predictions of general relativity regarding the decay of orbital energy due to gravitational radiation. If we observe a pulsar system that formed 10 billion years ago, would its observed orbital decay perfectly match the predicted rate based on current physics? The light validates the laws of physics across vast scales of time, showing that the rules governing our local movements were established in the universe's youth. The consistency of physical laws across billions of years is the ultimate reassurance, confirming that the history we read is encoded in a reliable language. The light from extremely distant, faint galaxies requires advanced image processing to remove noise and align the data for meaningful spectral analysis. If the processing algorithms introduced even a small systematic error, how would that artificially distort our derived history of the early universe's chemical state? Our interpretation of the deep past is always mediated by the tools we use, forcing a humble acknowledgement of potential systematic bias. The pursuit of light's history is an exercise in iterative refinement, continually stripping away the artifacts of our own observation process. The light from the sun, when observed over centuries, shows a cyclical variation in brightness linked to the waxing and waning of its magnetic field. If we could watch the sun's light from a planet orbiting a distant star, would we see the 11-year cycle imprinted clearly? Or would the distance smear it out? The short cycles of our local star are part of a longer, quieter history, reminding us that even immediate change is only visible against a vast, steady backdrop. The light teaches perspective. The frantic activity of the short term becomes mere texture against the immense, slow-moving canvas of cosmic time. The light emitted by molecular clouds in the Milky Way contains the spectral signature of complex organic molecules, the seeds of amino acids. If these molecules are found in the light from a galaxy that formed 5 billion years earlier, does that mean the chemistry of life arose almost immediately? The light suggests a universal predisposition for chemistry to organize itself toward complexity, an inherent drive within the laws of physics. The history of the universe is largely a history of increasingly complex chemical arrangements, illuminated by the light that records each stage. The light from distant gravitational lenses is magnified, allowing astronomers to resolve details in early galaxies that would otherwise be too faint to see. If that magnification allows us to see star formation in a galaxy 12 billion years old, are we looking at the galaxy's history or the history of the lens itself? The lens warps the image, but in doing so, it reveals a deeper history, the massive structures existing in the middle ground between us and the target. The light's journey is never simple. The history we read is always a composite, an intricate layering of intervening moments and structures. The light from the sun is essential for understanding the history of our own star, showing its current output relative to its younger, more active phases. If the sun were to suddenly flare with the intensity of a young star, would that intense burst of light carry a distinct, different chemical signature? We rely on the sun's current, relatively calm light to exist, unaware of the potential for past or future intensity that the light spectrum might reveal. The light of our own star is a constant reminder that even seemingly stable systems are merely pausing between dynamic historical phases. The light from a star in the galactic bulge travels through a denser stellar field, increasing the chance of obscuration by foreground dust clouds. If a galaxy's core is the oldest part, why is the light from that region so much harder to penetrate and analyze compared to the outer disk? The very center, the locus of the oldest stars, is often obscured by the collective dust created by those very stars during their intermediate lives. The history is often hidden by the consequences of that history, a self-imposed obscuration that demands patience to look beyond the immediate glow. The light from type Ia supernovae is used as a standard measure because they are thought to explode at nearly the same critical mass, leading to uniform luminosity. If the universe's expansion rate was different in the era when many of these supernovae exploded, would their resulting light curve shape appear distorted to us? The light is the key to mapping cosmic expansion, but we must constantly check if the standard candle itself is behaving identically across billions of years. The history of the universe is written in the reliability of its explosions, and any slight change in the event alters our perception of the timeline. The light from the most distant quasars suggests that the accretion process around early supermassive black holes was highly efficient. If that efficiency depended on the initial density of gas clouds, does the light tell us that the early universe was far more clumpy than current models suggest? The light exposes inconsistencies, hinting that the universe's first billion years involved processes far more dynamic and aggressive than our current expectations allow. The past, as revealed by light, is often more vigorous and impatient than the slow, steady evolution we observe in the relatively quiet present. The light reflected from the Martian surface shows a distinct signature of iron oxides, the result of geological processes stretching back billions of years. If we could see the light from Mars when its atmosphere was thicker, would the reflected spectrum show evidence of widespread surface liquid water? The light is a historical witness to our own planet's environmental evolution, documenting the slow loss of the conditions that once made life easier. The history of Mars, read in its reflected light, is a quiet warning that even stable environments are subject to the slow, inexorable turning of cosmic time. The light from a star approaching the supermassive black hole at the galactic center exhibits extreme relativistic effects as it nears the point of no return. If we could observe that star over several years, would the light show its spectral lines shifting dramatically as time dilation affects the photon emission rate? The light of that doomed star is stretched and distorted by the ultimate gravity, a final visible scream before it crosses the horizon of our history. Its history, viewed across the vast distance, becomes the ultimate demonstration of time's relativity, where movement toward oblivion dramatically alters the perception of its duration. The faint, diffuse light emanating from the space between galaxy clusters is called the extragalactic background light, a true measure of the universe's overall luminosity. If the universe is accelerating, the light from that background is continuously being dimmed and redshifted. meaning the EGL is constantly decreasing over time. The overall glow of the cosmos is a fading ember. The history we observe is brighter than the history that will be observed by future astronomers. We are living in the universe's brightest historical period, bathed in the collective light of 1 trillion stars, whose combined output will eventually decline. The light from M-dwarf stars, though faint, is incredibly stable and long-lived, offering the potential for very long-term historical continuity for any orbiting planets. If a planet orbits such a star for 100 billion years, what kind of history would its light reflect? A history of profound, unvarying stability. The light from such systems promises a quiet history, one defined not by dramatic stellar death, but by the slow, persistent unfolding of gentle evolution. Endurance, rather than brilliance, may be the true measure of significance in the long chronicle of cosmic history revealed by the steady light. The light from distant globular clusters, being composed of old, low-mass stars, suggests these systems have avoided major disruptive merger events. If they avoided mergers, does the light from these clusters preserve the closest analog to the initial conditions of the early Milky Way's stellar population? These isolated islands of ancient light are the stable archives, the untouched libraries holding the original, foundational texts of galactic formation. To study them is to search for the universe's signature of innocence, the state before contamination by the energetic chaos of later stellar life. The light emitted by an active galactic nucleus is often obscured by a thick torus of dust and gas, hiding the accretion disk from direct view. If that obscuring torus periodically opens up, does the brief glimpse of the core reveal a history of the black hole's activity that was otherwise masked? The light shows us that history is often revealed in momentary interruptions, brief openings in the darkness that offer access to concealed truths. We must learn to wait for the universe to momentarily lower its defenses, for the most intense stories are often held behind the deepest veils. The Doppler shift in light from a galaxy confirms its recession velocity, which, when combined with distance, determines the Hubble constant for that epoch. If the recession velocity is subtly different than predicted, does that imply that the local distribution of dark energy is not perfectly uniform? Even the grand expansion is subtly influenced by local gravitational irregularities, showing that the universal history is still shaped by local dynamics. The light reveals a constant negotiation between the universal tendency toward expansion and the local tendency toward clumping and structure formation. The light from a distant star that has passed near a neutron star shows a measurable gravitational redshift, confirming the space-time curvature in that region. If we could track that star for 1,000 years, would the increasing accumulated redshift tell us about the precise time it made its closest pass? The light becomes a highly sensitive ruler, measuring the gravitational geography of the space it traversed across the entire span of its history. The energy loss of a photon is a direct, physical measure of the density and gravitational history of the space through which it has journeyed. The light spectrum from terrestrial aurorae reveals the energy state of atmospheric molecules, a visible manifestation of solar wind interactions from the recent past. If we could isolate the light emitted from an aurora caused by a massive coronal mass ejection from the sun hundreds of years ago, what would its intensity be? The light is a delayed echo of solar violence, a beautiful display on Earth caused by an event that transpired long before our present concerns. Even the familiar, local light carries the news of its distant energetic origin, connecting our atmosphere to the turbulent history of our parent star. The light from the earliest molecular clouds in the universe contains the spectral signature of molecular hydrogen, the fuel for the first stars. If the formation of this hydrogen required a precise set of cooling conditions, does its presence in the light confirm that the early universe cooled exactly as predicted? The light confirms the fidelity of the foundational physics, showing that the universe adhered to its initial rules even in its nascent, chaotic state. The history written in light is fundamentally a confirmation of consistency, that the universe operates on dependable, measurable principles across all time. The light reflected from the dark side of the moon during an eclipse reveals the faint, reddish glow of light scattered through Earth's atmosphere. If Earth's atmosphere were far thicker, scattering more light, would the eclipsed moon appear brighter, revealing a different historical composition of our air? The light filtering through our air is a portrait of our own environment's current state, a self-reflection recorded by the shadow of our companion. The most profound historical record is often the one we generate ourselves, the light reflecting our immediate present condition back to us. The light from a distant globular cluster shows a clear main sequence turn-off point, allowing for a precise determination of the cluster's age. If that turn-off point is significantly different from our own local solar neighborhood, does that imply a vastly different initial chemical environment for the cluster? The light confirms that the history of star formation was not uniform. Some regions accelerated quickly into maturity, while others lagged behind in a slow burn. The narrative of the cosmos is not a single flow, but a collection of parallel histories, each illuminated by its own unique sequence of stellar births and deaths. The light from the cores of active galaxies, when viewed off-axis, is absorbed by the dusty torus, creating absorption features that map the torus's density. If the torus is dense, does that imply that the galaxy's history involved a massive, recent influx of gas and dust that fed the central engine? The obscuring dust is a sign of recent activity, a temporary shadow cast by the rapid consumption of matter near the black hole's luminous past. The shadows in the light tell a story of drama and consumption, revealing the most active periods of galactic history that are hidden from direct view. The light from a binary system, where one component is a main sequence star and the other is a white dwarf, shows a clear difference in surface temperature and color. If we track the light from the white dwarf over 1,000 years, would its temperature, and thus its color, change in a predictable way as it cools? The white dwarf's light is the chronicle of its slow, inevitable fade, a history of cooling that stretches for untold trillions of years into the future. Its light embodies infinite patience, a steady, measurable decline that proves that even the end of a star can be a long, drawn-out narrative. The light from the atmosphere of Jupiter shows absorption lines caused by ammonia and methane, chemical markers of its cold, deep atmosphere. If those chemical abundances have changed over the 4 billion years of the solar system, what does the current light signature tell us about that historical shift? Jupiter's light is an ancient, massive diary, recording the slow settling of the solar nebula's initial chemical chaos into its present, stratified state. The massive planets preserve the history of the beginning, their light confirming the steady gravitational distillation of matter from the primordial disk. The light from the most distant objects is so faint that current telescopes can only detect the collective emission from thousands of galaxies pooled together. If we could resolve the light from a single galaxy at that distance, what secrets of early structure formation would that individual illumination reveal? The collective light gives us the overview, but the individual photon carries the specific detail, a constant trade-off between breadth and depth in historical study. The universe's history is a mosaic. We piece together the grand picture from countless faint, isolated fragments that have survived the journey. The light from the accretion disk around a newly formed T-Tauri star shows evidence of powerful outflows clearing away the surrounding natal cloud. If the outflow clears the gas cloud, does the subsequent light from the star then become significantly less redshifted, revealing a sudden clarity in its history? The star's light transitions from being obscured by its own birth environment to shining freely, marking the end of one historical phase and the beginning of another. The moment a system clears its internal fog is when its true history can finally be broadcast without self-contamination. A moment of luminous honesty. The light from the sun, when analyzed for solar neutrinos, offers a history of its core fusion processes that is entirely independent of electromagnetic radiation. If the core processes change over billions of years, would the light spectrum show a corresponding change that is delayed by the light travel time from the core? The light of the sun carries the history of its deep interior, a layered record showing us the past state of the furnace that sustains our immediate reality. We are surrounded by history. Every visible beam from our local star is merely the most recent report from its ancient, churning heart. The light polarization from distant galaxies, when studied across billions of years, constrains the evolution of the universe's large-scale magnetic fields. If magnetic fields were stronger in the early universe, would the light from that era show a more pronounced, uniform alignment due to stronger field lines? The light chronicles the history of cosmic magnetism, showing how the unseen forces organize themselves from random fluctuations into grand, coherent structures. The history of light is interwoven with the history of force. The structure of space-time dictates how the messages of the past are finally shaped. The light emitted by an object moving rapidly away from us is subject to extreme Doppler shifting, pushing its spectrum far into the red or infrared. If that object were to suddenly reverse course and move toward us at the same high speed, what spectral transformation would its light undergo upon arrival? The light would transition from a whisper of the deep past to a shout from the immediate future, marking an almost instantaneous shift in its historical context. Motion is history in motion. The direction of a source dictates whether we receive its past message or its current pronouncement. The light from a stellar nursery, rich in heavy elements, implies that several generations of massive stars have already lived and died within that region. If we could observe the light from that nebula before the first generation died, would it appear almost entirely metal-free, a pure hydrogen glow? The nebula is a historical record of stellar productivity, showing the slow, deliberate enrichment of the environment by the deaths of its powerful ancestors. The light confirms that construction requires destruction. The foundation of all future complexity is laid by the explosive endings of the past. The light from the Kepler spacecraft, even years after its mission ended, continues to travel outward, carrying a history of observed exoplanet transits. If an alien received that light today, they would be seeing our analysis of distant worlds, a historical record of our own investigative effort. Our attempt to read history is itself part of the history being broadcast. Every image we take contributes to the light that will arrive later. We are caught in a feedback loop of light. The past illuminates the present, and the present sends its own faint light forward into the deep future. The light from a gravitational wave event, if it has an electromagnetic counterpart, provides a precise, localized anchor point in space-time for the event. If the light arrived slightly later than the wave, what does that temporal gap reveal about the physics governing the interaction between gravity and photons near the merger? The subtle timing difference between the two messengers, wave and light, is crucial for understanding the mechanics of space-time curvature during extreme events. The universe speaks through multiple channels, and only by carefully comparing the arrival times of these different historical records can we truly comprehend the event. The light from the distant universe is subject to extinction by intervening matter, making corrections necessary to estimate the intrinsic luminosity of the source. If the extinction varies, does that imply that the density of matter distribution in the universe was much higher in the past than we currently model? The obscuring dust is a historical marker in itself, suggesting epochs of high star formation and subsequent enrichment that we can only trace indirectly. The light that struggles the most to reach us often carries the most compelling evidence about the tumultuous, formative periods of cosmic structure. The light from a white dwarf that has been accreting matter from a companion star will show unusual spectral features as the surface composition changes. If the accretion rate changes, does the light signature shift rapidly, providing a high-resolution history of the star's recent consumption patterns? The light records the physics of symbiosis, one star living off the borrowed history of its fading companion, their joint light telling a complex, intertwined narrative. Even in a binary system, the light weaves two separate histories together, forcing the observer to untangle which story belongs to which celestial actor. The light reflected from Earth, when observed from the Moon, is significantly fainter than the sunlight directly illuminating the Moon's surface. If we could observe the Earth's reflected light over billions of years, what changes in its color would indicate the slow, historical shift in ocean coverage? The light holds the history of our planet's breath, the gradual transformation of its atmosphere and surface chemistry across deep geological time. The reflected light is the Earth's biography, written in subtle shifts of color that only the most patient observer, aided by time, can fully decipher. The light from a massive spiral galaxy shows distinct streaming patterns in the outer halo, evidence of past, smaller satellite galaxies being torn apart. If we trace those light trails backward in time, do they converge on the location of the smaller galaxies whose light we can no longer see distinctly? The light paints a picture of cosmic cannibalism, the history of the massive galaxy written in the stretched-out trails of those it has absorbed. The structure we see is a scar, a luminous testament to the violence of accretion, showing that the past is never truly erased, only smeared across the light. The light from the sun, when analyzed by a spectrometer, reveals the presence of helium, a signature of the nuclear fusion processes occurring in its core. If the sun's fusion rate slows down over its lifetime, would the resulting light show a progressive change in the observed helium abundance as time passes? The light tells the story of energy conversion, documenting the sun's slow, steady transformation of matter into the light that sustains our local history. Our entire existence is framed by the light of this process, a continuous flow of energy derived from an ancient, sustained nuclear performance. The light from the earliest epochs of galaxy formation is highly fragmented, requiring careful consideration of foreground contamination from foreground stars. If a faint, ancient galaxy is truly isolated, its light signature should be utterly distinct. How do we confirm that lack of contamination across light years? The confirmation requires immense effort, ensuring that the history we attribute to the deep past is not merely a misidentified feature from a much closer, recent time. Reliable history demands vigilance against the intrusion of the near past, ensuring the integrity of the faint, ancient signal is maintained. The light reflected from Jupiter's Great Red Spot shows the absorption signature of various chemical compounds, hinting at the cloud layer dynamics. If that storm has raged for centuries, does the light we see today show chemical differences compared to the light from the storm's earliest recorded appearance? The light records the chemical history of an enduring weather event, showing how energy is sustained and how atmospheric composition evolves over long timescales. Even on a gas giant, the light confirms that no process is truly static. Everything changes, albeit on a temporal scale far exceeding our normal measure. The light from quasars is so immense that it can outshine the total combined light of all the stars in their host galaxy by a factor of hundreds. If the host galaxy's history is dominated by the light of its central engine, what historical evidence of the galaxy's own slow evolution can we still extract? We must learn to filter the shout of the quasar, to hear the quiet, enduring murmur of the older stars that surround it. The galaxy's true antiquity. The brightest light often tells the most recent, dramatic story. But the deepest history resides in the fainter, steadier emissions that have traveled the longest. The light from a star that has passed through the galactic plane shows signs of scattering and reddening due to the increased density of intervening dust. If we could see that star's light before it entered the plane, would its spectrum reveal a purity of composition that the current, scattered light obscures? The galactic plane is a threshold in time. Crossing it alters the light's message, introducing a layer of local, recent environmental history. The journey through the plane is a necessary distortion, forcing us to recognize that the light's message is always co-authored by its surroundings. The light from the most massive stars in a cluster shows they have exhausted their core hydrogen much faster than their lower mass counterparts, confirming stellar lifespan theory. If we see a very old, massive star that should have already died, what does its light tell us about the physics that allowed it to sustain fusion for so long? Such a survivor challenges our established timeline, suggesting that nature found a loophole, a temporary exception to the rule of rapid, brilliant stellar consumption. The light confirms that the history of the universe is not a rigid, clockwork process, but one punctuated by rare, enduring anomalies that defy the general trend. The light from the early universe, the CMB, shows tiny anisotropies, temperature differences that originated from quantum fluctuations during inflation. If those initial quantum jitters dictated the structure of all galaxies, does the light reveal a deep, underlying quantum connection between all distant objects? We are fundamentally linked to those earliest, subatomic flickers. The light confirms that the grandest history began at the scale of pure probability. The entire cosmic saga is rooted in the delicate, fleeting uncertainty of the very first moments, proving that history springs from the edge of chaos. The light emitted from the accretion disk of an intermediate mass black hole shows high velocity and intense X-ray emission, indicative of rapid growth. If the accretion process is violent, does the resulting light carry a spectral signature indicating that the consumed matter was largely pristine, heavy element poor material? The light records the consumption of the old to fuel the new central engine, a continuous cycle of cosmic digestion and renewal. The universe's history is defined by this process, the bright, chaotic feeding of the centers, illuminating the slow accumulation of material around them. The light from an exoplanet's atmosphere, when analyzed during transit, can reveal the presence of water vapor, a key marker for potential habitability. If that water vapor signature is strong, does that imply that the planet has maintained stable liquid oceans across the entire historical period the light has traveled? The light offers a momentary confirmation of stability, suggesting that for this specific world, the cosmic forces have allowed for a long, relatively unchanging phase. In the vast sea of cosmic change, the light from a steady, wet world is a profound counterpoint, a history of constancy against the backdrop of flux. The light from a nearby supernova remnant shows the expansion velocity of the shock wave, derived from the Doppler shift of the ejected material. If we track the light of that shock wave over centuries, how accurately can we determine the initial explosion parameters based on its current deceleration? The light provides the final metrics of a spectacular past event, allowing us to reverse engineer the force and scale of the stellar death that occurred long ago. The history of violence is never truly lost. It is simply transformed into the measurable, receding light of the expanding aftermath. The light from a distant gravitational lens is subject to time delays between the multiple images, providing a measurement of the mass distribution in the foreground lens. If the light from one image arrives years before the other, what does that time difference tell us about the gravitational geometry of the foreground cluster during that entire period? The light splits the history of the source into separate narratives, each one arriving at a different time, dictated by the mass it encountered on its varied paths. The path of light is a physical manifestation of gravitational history, showing that even a single event can be perceived in multiple temporal slices. The light from the sun, when passing through the solar corona during an eclipse, is slightly polarized due to the scattering by free electrons in the hot plasma. If the polarization angle shifts over the solar cycle, does that light carry a history of the magnetic field strength on the sun's surface during that time? The light records the sun's magnetic temperament, showing the waxing and waning of its unseen forces as documented by the slight twist in its own radiance. Our immediate star broadcasts a complex history, one layered with energetic fluctuations that subtly shape the very light that illuminates our present. The light from the most distant known structures is so severely redshifted that the UV emissions from their early stars have been stretched into the radio spectrum. If we could see that light in its original UV state, would it reveal star formation activity much more vigorous and immediate than current redshifted analysis suggests? The light is muted by expansion, forcing us to extrapolate the violence of the early universe from signals that have been softened across billions of years. The true historical intensity of the universe's beginning is hidden behind the redshift veil, a fiery past muted by the steady cooling of expanding time. The light from quasars, when observed over a decade, shows slight variations in position, suggesting the light source is a compact object near the central black hole. If that variability maps the orbit, does the light carry the historical record of the orbital mechanics that governed that extreme environment billions of years ago. The light confirms that even around an abyss, order persists. The mass dictates a path, and the light faithfully records the execution of that path. The history of the quasar is written in the wobble of its own light, a visible manifestation of the gravitational dance occurring at its very core. The light from the sun, passing through the Earth's atmosphere, is selectively absorbed by ozone, leaving a unique spectral fingerprint indicating the ozone layer's presence. If we observed Earth's light history from afar, would the historical shift in ozone levels from zero to current levels be clearly discernible in the spectrum? The light acts as an environmental barometer across time, showing the slow, historical construction of our protective atmospheric shield through the interaction of sunlight. The light confirms that planetary history is a process of emergent complexity, where simple forces gradually build up the conditions necessary for sustained life. The light from the most distant clusters appears highly elongated and distorted due to the cumulative gravitational lensing effect of all intervening dark matter. If we could reverse the lensing effect perfectly, would the distant cluster snap back into its original, compact form as it existed billions of years ago? The light shows us the universe under stress, bent and stretched by the massive structures that hold it together. A history written in curvature. The shape of the light is the shape of the intervening mass. The distortion is not an illusion, but the most accurate map of past gravitational influence. The light from the sun, when observed over long periods, shows that its overall luminosity has increased by about 30% since its formation. If Earth's history is read in the sun's changing light, what does that past increase in energy imply about the ancient stability of our oceans and climate? The light confirms that our planet has been navigating an increasingly energetic environment, a slow historical climb in solar intensity that shaped our biology. The star that sustains us is itself evolving, and its light carries the history of that long, continuous chemical transformation across its main sequence life. The light from the earliest detectable galaxies shows a surprising abundance of short-lived, massive stars, indicating rapid chemical enrichment cycles. If these massive stars died quickly, did their brilliant light completely ionize the surrounding gas before the next generation had time to form in that local volume? The universe's early history was one of rapid cycles, brilliant creation followed by explosive recycling, quickly building up the heavy elements necessary for planets. The light reveals that the universe learned to create complex structure rapidly, prioritizing mass and energy expenditure in its fiery youth. The light from a star that has shed its outer layers into space forms a planetary nebula, a glowing shell of enriched material illuminated by the hot core. If we could watch that nebula expand over millennia, would the light show the dispersal of its enriched material across the vastness of the interstellar medium? The nebula is the final letter from a dying star, a generous distribution of the heavy elements it painstakingly forged during its long, quiet life. Its light carries the ultimate gift, the material history of its own existence, now seeded into the future fabric of new stellar nurseries. The light from the Andromeda galaxy, traveling towards us, will one day show the effects of its gravitational interaction with the Milky Way's own halo. If we could watch the light from that collision over 100 million years, would the merged system show a distinct, brighter pattern of star formation? The light records the final cosmic merger, a slow-motion reconciliation of two immense structures whose histories are now destined to become one unified narrative. The light confirms that even when individual histories end through collision, the resulting structure carries the combined, altered memory of both progenitors. The light from exoplanets that transit an M-dwarf star is particularly useful because the small star provides a deep, high-contrast dip in brightness. If that faint, ancient light reveals an Earth-sized planet, does that imply the early universe was capable of forming rocky worlds around even the smallest stars? The light suggests that the potential for complexity is ubiquitous, not reserved only for the massive, brilliant, short-lived stellar environments. The history of the universe is written in the faint gleam of countless worlds, confirming that life's ingredients are scattered widely, waiting only for time. The light from the earliest galaxy survey fields shows a relatively low star formation rate compared to the peak observed several billion years later. If the rate was slower, does the light from that time suggest that the early universe was less chemically evolved, holding fewer heavy elements for planet formation? The early history was one of slow accrual, where the building blocks for future complexity were being created at a measured, deliberate pace. The narrative of star birth is one of acceleration, a slow start giving way to a brilliant, energetic middle period before the inevitable decline. The light from the Crab Nebula remnant shows high-energy X-rays, indicating the presence of a rapidly spinning neutron star spinning down over millennia. If the pulsar's spin rate is slowing, does the varying X-ray emission record the history of its magnetic field decay across its observed lifetime? The light traces the gradual deceleration of a stellar corpse, a story of energy dissipation that unfolds with a slow, majestic certainty. The history of these stellar remnants is one of relentless surrender, giving up their rotational energy in pulses of light until they finally fall silent. The light from planetary surfaces, when observed in infrared, reveals thermal inertia, how quickly the surface heats up and cools down after stellar illumination. If a planet's light shows slow thermal response, does that suggest a history of thick atmospheres or vast oceans? Mechanisms that stabilize temperature over time? The light records the thermal memory of a world, the lingering warmth or cold that persists long after the immediate source of energy has passed. Stability is written in the sluggish response of light. It is the quality of endurance that allows for the long, slow development of complex systems. The light from the very edge of the observable universe is the limit of our historical retrieval, representing the earliest moments accessible by any physical means. If the universe continues to expand, will the light from objects currently near that edge become permanently redshifted out of existence for future observers? The universe is actively erasing its own record. The current generation of observers has a unique, fleeting privilege to witness the most ancient history. Our historical window is finite. The light we see now is the brightest and most complete record we will ever possess of the universe's absolute beginning. The light polarization from distant galaxies shows a slight correlation with the large-scale structure, hinting at subtle field effects during early assembly. If magnetic fields directed the flow of early matter, would the light from those initial structures show a non-random orientation across the entire sky? The light confirms that the history of structure was guided by unseen forces, long before the first stars had the power to shine visibly. The true architects of cosmic history are those forces that act upon the light before it is even emitted, shaping the message itself. The light from an exoplanet in a retrograde orbit around its star reveals a complex history of gravitational interaction and orbital flipping events. If we could rewind the light to see the star system's initial configuration, would the planet's current retrograde path appear as a historical anomaly or a common outcome? The light records the history of gravitational tugs, showing how planetary systems can be chaotic and unpredictable, yet still evolve into a seemingly stable state. Stability, when viewed across cosmic time, is revealed not as stillness, but as the complex, enduring pattern forged from initial, violent perturbations. The light from a star recently discovered in the galactic halo shows the expected low metallicity, suggesting it formed very early in the galaxy's history. If that star survived for 13 billion years, what unique evolutionary path allowed it to maintain its low chemical complexity despite galactic evolution? It is a lone survivor, a quiet witness that has maintained its pristine state while the surrounding galactic environment dramatically changed its chemical character. The light from these ancient beacons reminds us that history is not monolithic. There are deep time narratives unfolding in slow motion, preserved in purity. The light from a distant galaxy cluster's central dominant galaxy shows strong evidence of ongoing mergers, indicated by disturbed tidal tails in the surrounding light. If we could see the light from the smaller galaxies before they were absorbed, would we detect a coherent, independent history that is now lost in the merged light? The light traces the doom of those smaller galaxies, showing their stars being stretched into long, fading strands that feed the central giant. Their individual histories do not vanish. They are merely incorporated into the grander, slower narrative of the larger, dominant light source. The light from the early universe, post-recombination, shows a remarkable lack of structure, suggesting a very smooth distribution of initial density perturbations. If the universe was so smooth, then what tiny, fleeting instability was magnified over billions of years to create the vast, clumpy structures we see now? It speaks to the immense power of tiny differences, how an almost negligible variation in the early light dictated the entire course of cosmic history. The history of everything rests upon an almost imperceptible imperfection, a microscopic flaw in the original luminous perfection of the beginning. The light from a white dwarf star, having cooled significantly over billions of years, eventually sinks below the threshold where it can be detected as visible light. If that star's light finally fades entirely, does its history, the fusion it performed, the elements it created, cease to exist in any observable form? Perhaps the ultimate fate of every historical record is to dim into the background, becoming indistinguishable from the silence that preceded its emission. The memory of a star is not eternal. It is subject to the same fading process as any ephemeral message carried across the immense, dark gulfs. The light polarization from the sun's corona reveals the structure of its magnetic field, which dictates the paths of charged particles ejected as solar wind. If the solar wind carries planetary material away, does the light record subtly alter over time as the sun consumes the history of its own close neighbors? The sun's light is a record of consumption, showing how it continuously replenishes its mass by absorbing the material of the younger, closer worlds around it. Our life is sustained by the star's history of ingestion, a constant flow of borrowed matter transformed into the light that defines our immediate present. The light from objects receding due to dark energy shows a continuous stretching of space-time that occurs uniformly across all measured distances. If the stretching rate changes in the far future, how will the light from objects currently visible be distorted, making their history appear faster or slower? The expansion rate itself is a historical variable, one that dictates how quickly the universe will eventually lose its ability to communicate across its own vastness. The future of light is one of increasing isolation, where the historical messages from distant shores will arrive weaker, slower, and eventually never at all. The light from the earliest galaxy clusters, seen via deep field surveys, confirms that gravity effectively assembled matter into immense structures early on. If gravity was so effective early on, what was the initial density fluctuation that provided the necessary seeds for that initial rapid assembly? The structure of the cosmos is a direct consequence of those initial, nearly invisible seeds, a testament to the power of tiny, sustained influence. The history of the universe is a continuous amplification of small initial conditions, where every moment builds upon the faint light of the one before it. The light from an asteroid orbiting the Sun shows seasonal variation in albedo as dust settles or is vaporized by solar heating over the orbital path. If we observed that asteroid from a distant star, would the light show a consistent, averaged history? Or would the faint seasonal variations still be discernible? The light of local history is often too nuanced for distant observation. Only the broad, massive events manage to pierce the intervening void with their signature. Our local, granular history fades quickly into the background noise. Only the brightest, most energetic narratives achieve true interstellar longevity. The light reflected from the icy surfaces of Kuiper Belt objects shows a distinct chemical composition related to the primordial solar nebula material. If we could analyze the light from these surfaces in extreme detail, would we find spectral evidence of bombardment by heavier material ejected from the inner solar system long ago? The outer remnants are the cold archives of the solar system's turbulent youth, preserving the chemical history of early, violent collisions. Their cold, reflected light confirms the chaotic, formative era, showing that the history of our home began not with order, but with energetic disruption. The light emitted by a star nearing the end of its life swells in size, increasing its surface area, although its surface temperature generally decreases. If we see a star whose light is disproportionately bright for its calculated low temperature, does that imply a recent, unrecorded mass accretion event? The light reveals a star struggling against the established timeline, a brief resurgence of activity before it yields to the inevitable cooling fate. Even the slow death of a star is marked by brief, confusing flares, moments where the past history momentarily conflicts with the present emission. The light from distant, high redshift objects is essential for constraining the history of dark energy, as the expansion rate was lower in the past. If dark energy's influence has grown over time, does the light show that distant galaxies were receding slower in the past than they are now? The light confirms that the universe's ultimate destiny, eternal expansion, is a historical development, not a constant feature of its initial state. The history of expansion is not linear. It is a dramatic curve, accelerating only recently, meaning the universe's past was far more structured than its future suggests. The light emitted by objects close to the event horizon of a black hole is severely redshifted by the immense gravitational potential well. If we could see that light blue shifted back to its emission frequency, would it appear almost infinitely energetic, representing the maximum energy density possible? The gravitational redshift is the universe's way of saying that energy comes at a cost. The deeper the potential well, the lower the energy of the escaping light. The history of light near a singularity is a history of loss. The energy spent escaping the boundary, defining the ultimate edge of our observable past. The light reflected from the surface of Pluto shows spectral evidence of frozen nitrogen and methane, remnants of the solar system's cold outer formation disk. If those volatiles are being slowly depleted by solar radiation, does the light show a historical decrease in the abundance of frozen nitrogen over time? Pluto's light records the slow, cold decline of the primordial material, a history of slow depletion played out across the vast outer reaches. Even the dimmest objects hold a history, one measured not in brilliance, but in the slow, patient accumulation and subsequent depletion of surface molecules. The light from the first stars, if ever detected, would provide a chemical baseline against which all subsequent heavy element production could be measured. If those first stars were indeed massive, would their light signature show evidence of immediate, powerful feedback mechanisms that shape the next generation? The first generation sets the stage for all subsequent history, their brief, intense lives scattering the necessary materials for complexity across the nascent universe. The true history of the cosmos is a chain reaction, initiated by the brilliance of the first light sources whose echoes we seek today. The light from galaxies showing high star formation rates indicates a high density of gas and a relatively low velocity dispersion in the local environment. If we look back to the peak star formation era, would the light show that galaxies were significantly smaller and more irregular at that time? The light confirms that the universe's history involves an explosive youth of creation, a period where building large structures happened with great velocity. The historical record is clear. The universe was more vibrant, more actively engaged in creation during its earlier epochs than it is in our current, quieter time. The light from the sun, when passing through the Earth's upper atmosphere, is slightly polarized by the scattering off-atmospheric molecules. If we could observe this polarization from a non-Earth-like planet, would the resulting angle tell us about the historical density of that alien atmosphere? The light carries an imprint of the environment it traverses, making every beam a miniature historical record of the medium through which it has passed. We must learn to read not just the source's light, but the story written by the space and the air that the light was forced to travel through. The light emitted by a distant galaxy is subject to extinction by the dust in the foreground galaxy cluster through which it must pass to reach us. If we could correct for this extinction perfectly, would the true, unreddened light reveal a history of star formation that was far more blue and intense in that ancient cluster? The dust is a historical blanket, covering the fiery youth of ancient structures, leaving us to infer their true intensity from the dimmed light that finally escapes. The history of clarity is preceded by a history of obscurity, where the most energetic events are often the hardest to fully perceive due to their own byproduct. The light from very distant quasars, being so energetic, occasionally shows evidence of strong gravitational lensing by intervening foreground galaxies. If the light path is severely warped, does that lensing itself provide an estimate of the mass and history of the galaxy doing the bending as it existed billions of years ago? The history of the foreground object is revealed not by its own light, but by the way it has manipulated the light coming from an even older, distant source. The universe teaches a lesson in indirect history. Sometimes the clearest view of the past is gained by observing the effect on a distant messenger. The light from our sun, when reaching Neptune, is only 1 part in 4 billion of the intensity it possesses here on Earth, due to the inverse square law. If we could observe Earth's reflected light from Neptune's orbit, what subtle spectral changes would reveal the historical evolution of our own planet's oceans? The history of our world is written in the faint, returning light, a history that requires immense patience to observe even across the confines of our own solar neighborhood. Distance is the ultimate context. It forces us to slow down, to see the slow accumulation of change rather than the fleeting nature of the immediate moment. The light emitted by an aging star shows a slight spectral shift toward the red as its core contracts and the surface cools, signaling the end of its main sequence. If that light carried a message about the star's entire life, what crucial piece of information would be encoded in the final, reddened photons? The final light seems to carry a message of acceptance, a quiet declaration that the process, however violent or gradual, has reached its natural conclusion. The end of a star's light is not a cessation of history, but a transition into a new, quieter phase, where the memory continues in the diffused nebula. The light from the early universe, before the first stars, should have been composed almost entirely of hydrogen and helium spectral lines, with no heavier elements. If we detect iron or carbon in the light from a galaxy that formed only 1 billion years after the Big Bang, what does that imply about the first star lifetimes? The presence of heavy elements is a historical anomaly, a sign that the violent, rapid life cycle of massive stars occurred even earlier than we theorized. The light confirms that the creation of complexity is an urgent process in the universe, a relentless forging of heavier materials even in the earliest, chaotic times. The light from a star in the galactic halo can be used to constrain the extent of the Milky Way's dark matter halo, as the star's velocity is governed by it. If the halo's dark matter distribution is mapped through these ancient stars, does the light reveal a history of gravitational mergers with smaller satellite galaxies? The halo's light acts as a gravitational tracer, mapping the past incursions and absorptions that have slowly built up the bulk of our galaxy's mass. The history of our immediate cosmic neighborhood is written in the motions of its oldest, faintest light sources, guided by unseen matter. The light from an active galaxy that has recently ceased its feeding phase shows a rapid drop in the emission from the accretion disk. But the older stellar light remains. If the light of the black hole's activity fades, how long will it take for the older, steady light of the surrounding stars to become the dominant historical signal? The galaxy transitions from a history dominated by the central engine to a history defined by the patient evolution of its surrounding stellar populations. The light shows us that all dramatic events eventually yield to the slow, steady processes of stellar aging, a return to quiet, predictable history. The light reaching us from Mars is today carrying information about its weather patterns from roughly 12 to 20 minutes in its own past. If the surface of Mars were to suddenly show signs of liquid water, how long would it take for that historical change to be confirmed by the returning light? The delay emphasizes that our observation of other worlds is always history. We can never witness a process unfold in real time across that small distance. The light is the ultimate proof that proximity does not eliminate the necessity of patience. Even the nearest historical events demand their due travel time. The light emitted by the first generation of stars, population 3, should have no absorption lines from heavy elements, only the pure signature of H and He. If we find even a trace of carbon in the light from a structure at Z, $10. Does that imply that the initial cooling and structure formation was much faster? Any hint of complexity in that earliest light suggests an accelerated timeline, a universe that began constructing its final narrative far sooner than expected. The history of the cosmos is not a gentle curve. It is punctuated by moments where light reveals an unexpectedly mature state in its youth. The light from a globular cluster shows an age older than the expansion age of the universe, derived from certain cosmological models. A historical tension. If the stars are indeed older than the universe's calculated age, which history must we trust? The steady expansion model, or the ancient light's testimony? The light presents a profound challenge to our timeline, forcing us to reconsider the very moment the cosmic history officially began. When light testifies to a history older than the framework built to measure it, the framework itself must yield to the evidence of the ages. The light from a distant galaxy shows a strong emission line, redshifted by Z's $11.5, placing it firmly in the early epoch of galaxy assembly. What quiet, unseen processes were happening in the dark matter halos that allowed this light source to ignite with such intensity so early in time? We are looking at a time when the universe was still figuring out how to arrange its components, and this galaxy is a sudden, bright answer to that question. The light confirms that structure found its footing quickly, suggesting a universe that was far more proactive in its self-organization than a purely passive expansion. The light from a star that has recently absorbed a planet will show an unusual, brief enrichment of heavy elements in its spectral lines. If that absorption event happened 100 years ago, would the light arriving now show the resulting chemical mixing? Or is the effect too subtle to measure? The light records the star's slow digestion of a world, a process that takes time to manifest chemically, showing that even sudden events have a delayed resonance. The history of stellar evolution is one of continuous incorporation, where the light gradually reveals the fate of the smaller objects consumed by the larger one. The light from a background quasar, when lensed by a foreground galaxy, is used to map the internal velocity dispersion of the lensing galaxy's stars. If the quasar's light took an extra 100 years to travel one path compared to another, would that time delay reveal a precise, historical map of the internal mass? The light provides a slow-motion, gravitational X-ray of the foreground galaxy, revealing the motions and mass distribution that existed at the time the light began its journey. The history of a galaxy is preserved in how it warps the light passing through it, making the distortion itself the most truthful historical document. The light from a pulsar that has been observed for decades shows subtle timing deviations, potentially caused by the orbital motion around an unseen companion. If the companion is another neutron star, does the light record their slow orbital decay as they radiate energy away via gravitational waves over the eons? The light traces the long, slow death spiral of two massive stellar cores, a history of energy loss, visible only through the rhythmic pulsing of the surviving lighthouse. Their combined light tells a story of finality, a predictable convergence dictated by the inexorable laws of gravity and energy conservation across deep time. The light from the Milky Way's disk, when viewed from beyond, reveals the steady rotation of its spiral arms, a motion sustained by its immense central mass. If we could watch the light from the arms over 1 billion years, would the rotation speed remain constant? Or would the light show the effect of increasing dark energy resistance? Our galaxy's history is a dance of inertia and expansion, a visible struggle between the forces that bind its stellar population and those that pull it apart. The light confirms that structure is transient. Even a massive galaxy is merely a temporary concentration of mass, destined to be affected by the universe's cooling end. The light from Jupiter's moon Io shows intense volcanic activity caused by the tidal stresses from Jupiter's massive gravitational field. If we could see the light from Io from 1 billion years ago, would the volcanic signature be fainter, suggesting a less intense tidal history with Jupiter? Perhaps we search too hard for the grand cosmic story, when the true lesson lies in the small, persistent histories of worlds simply trying to survive. The light from Io is a quiet testament to endurance, a history written in molten rock, showing that persistence is found even in the most violent orbits. We are small observers standing in the present, yet we hold the luminous record of worlds that have struggled through eons just to maintain their steady glow. To understand the universe is to find peace in the knowledge that every little thing that struggles to exist leaves a faint, precious signature in the light. The light from distant quasars, when analyzed for spectral variability, offers clues about the density and temperature of the intergalactic medium at that ancient time. If the intergalactic medium was much hotter in the past, would the quasar light have been scattered differently, leading to a different overall spectral profile? The history of the space between things is as important as the history of the objects themselves, written in how the light is attenuated. The emptiness between the luminous beacons is not void. It is a historical substance, shaped by the energy and matter that has passed through it across time. The light from a stellar nursery shows ongoing gravitational collapse, the process by which clouds condense into protostars that will eventually shine. If we could see that light from 1 billion years in the past, would the process of collapse appear faster, driven by higher initial gas density? The light records the entire life cycle, from the slow, cold gathering of dust to the final, brilliant ignition, a narrative of inevitable emergence. The universe constantly strives to create light, to turn the cold potential of the dark into the active, traveling confirmation of its own existence. The light from the sun shows a slight, long-term increase in luminosity due to the slow conversion of hydrogen to helium in the core over billions of years. If the sun were only half its current age, would its light show a distinctly lower flux, implying a cooler, potentially less volatile environment for early Earth? Our history on this planet is intrinsically tied to the slow, measured increase of our star's energy output, a historical tide affecting all life. The light of our own star is a constant narrative of change, proving that nothing, not even the steady center of our world, remains truly fixed across time. The light from an exoplanet orbiting a neutron star would be extremely faint, requiring incredibly sensitive instrumentation to analyze its atmospheric composition. If that planet has a thick atmosphere, Would the light reveal chemical markers indicative of intense tidal stresses or extreme gravitational forces acting on its surface? The light from such a world tells a history of near destruction, a world living under the constant crushing weight of a stellar remnant's profound gravity. Life's history, even under such duress, might be possible, suggesting that persistence can carve out a niche even in the universe's most inhospitable epochs. Perhaps the true meaning of the ancient light is not about the stars it shows, but about the persistent, quiet human urge to keep looking up at all. The act of observation itself, the decision to seek what is distant and old, is the only truly meaningful gesture in the face of infinite, indifferent time. We search the past for answers, but we find only the structure of the question, the enduring human need to place ourselves within the grand unfolding. The light ceases to be information and becomes invitation, an invitation to continue the dialogue that began before our world even had time to form. The light from the center of a spiral galaxy reveals a high concentration of older, redder stars clustered tightly around the central gravitational potential. If the center is the oldest region, what light signature would we observe if we could see it before the first massive stars had completed their rapid evolution cycles? The core's light is the history of density, showing where matter has congregated and aged most profoundly. The galactic anchor point for deep time. The center holds the galaxy's memory in its oldest stars. Their faint, patient light, the most reliable witness to the system's own genesis. The light from Earth, reaching an alien civilization, would show the historical evolution of our atmosphere, particularly the rise of molecular oxygen in the Proterozoic. If that civilization were to receive our light from that era, would they interpret the sudden oxygen spike as a catastrophic pollution event or a sign of life? Our planet's history, viewed from afar, is a story of chemical warfare followed by biological equilibrium, all encoded in the light we passively transmit. The light carries the undeniable proof of our struggle, showing an external observer the long path we took from simple chemistry to self-aware reflection. The light from a distant magnetar shows an intense, highly polarized gamma ray burst, indicating an extreme magnetic field that has twisted the escaping photons. If the magnetar's field decays over a few thousand years, would the light received today show a significant loss of polarization compared to the light from a millennium ago? The light captures the star's decay, showing the slow untangling of its immense magnetic force, a history written in the alignment of energy itself. The history of magnetic fields is one of inevitable relaxation. The intense forces forged in stellar collapse eventually yield to the long, slow passage of light time. The light from the earliest known quasars suggests that the supermassive black holes driving them were already massive when the universe was less than 1 billion years old. If they grew that fast, what light signature would we expect from the massive primordial gas clouds they must have consumed so voraciously in those first eons? The light tells a story of rapid, early construction, suggesting the universe was not hesitant, but aggressively sought to build its largest gravitational anchors immediately. The history of mass aggregation is one of early, explosive growth, where the greatest structures were established before the universe had settled into its calmer, mature phase. We must accept that the universe's most formative moments are often the most hidden, glimpsed only through the distorted, time-delayed signals of their immense aftermath. The true wisdom is realizing that the most beautiful histories are the ones that required the most effort, the light that fought the hardest to reach us. It makes the observer feel small, yet privileged, an inheritor of a legacy written in light across unimaginable spans of silence and time. The quiet contemplation of the distant light is perhaps the closest we can come to touching the eternal, the profound, the always has been. The light from a distant star cluster shows a clear sequence of stellar evolution, where the most massive stars have already exhausted their fuel and died. If we could see the light from those massive stars before they died, would we see a period of intense, rapid heavy element production that shaped the cluster's history? The light records the cycle. Brilliant, swift youth leading to necessary, explosive death, providing the raw material for the next, quieter generation of stars. The entire history of the cluster is visible in the differing colors of its inhabitants, a spectrum of life stages laid bare by the slow arrival of light. The light from a distant star cluster shows that the chemical fingerprint of its stars is slightly different from that of its neighbors, implying different formation histories. If the chemical difference is due to absorbing gas from a nearby, chemically enriched supernova remnant, does the light trace that past interaction? The history of a cluster is influenced by its neighbors. The light carries the scars of gravitational interaction and the mixing of enriched interstellar material. Nothing exists in isolation in cosmic history. Every light source is a participant in a vast, slow exchange of matter and influence across the void. The light from the sun, when observed from the boundary of the Oort cloud, is so faint that it would appear as a dim, distant star, not a blazing source. If that faint light carries the history of the sun's activity over the last year, how would a massive solar flare from that time manifest when finally detected? The history of our local star is told in moments of quiet dimming and brief, sudden outbursts, a pattern that only becomes clear over long periods of observation. The star's long life is a compilation of countless tiny events, with the grandest moments being those that manage to leave a long-lasting signature in the light. The light from the most distant known galaxies confirms that the universe contains surprisingly complex star-forming regions at Z $10. If the stellar populations were already complex, what did the light of the very first generation of stars, the ones that seeded this complexity, look like? We search for the purity of the beginning, the light that existed before complexity, hoping to find the ultimate, simple message that started the long chronicle. The quest for that first light is the philosophical anchor of our endeavor, to touch the moment when the universe first decided to narrate its own unfolding. The light from a distant quasar shows a pattern of absorption lines from intervening gas clouds, each cloud marking a specific distance and epoch in time. If we could precisely map the location and density of those absorbing clouds based on the light, would we have a three-dimensional map of the universe's past gas distribution? The light turns every intervening cloud into a historical marker, transforming the empty space between galaxies into a vast, layered map of matter distribution. The history of the cosmos is written not just in the bright sources, but in the shadows they cast, the spectral evidence of everything that stood between then and now. The light emitted by the sun during a solar minimum shows a reduced output of energetic particles, indicating a period of magnetic quiescence in its history. If that low activity phase persisted for longer than usual, How would the subtle change in the sun's light output affect the long-term climate history of Earth? The light of our star carries the historical record of its magnetic mood swings, subtle variations that dictate the fate of the small world revolving around it. Our immediate history is tied to the temperament of our nearest source, showing that the grand scale of the cosmos is reflected in the quietest local rhythms. The light from a supernova in a distant galaxy cluster is magnified by the cluster's gravity, allowing us to study the event in unprecedented detail. If the magnification varies across the different light paths of the lensed images, does that reveal a time-varying density in the foreground cluster's dark matter? The light carries the evidence of the bending structure, allowing us to map the past distribution of mass in the foreground cluster based on how it distorted the background event. The history of mass is written in the distortion of light. The shape of the image is the truest map of the gravitational influences it traversed. The light from the very first generations of stars, if captured, would show spectral lines dominated entirely by hydrogen and helium, a pure cosmic signature. If we found a heavier element in that light, what revolutionary conclusion would that force upon our understanding of the universe's timeline for chemical enrichment? The purity of that hypothesized light represents the ultimate historical baseline, the simplest state from which all subsequent chemical complexity arose. The history of the universe, seen in its purest light, is the story of how simplicity inevitably gives way to the richness of layered atomic arrangement. The light reflected from the surfaces of the Galilean moons reveals their varied geological histories, from the active volcanism of Io to the ancient ice of Callisto. If we could see the light from Io from the time the Galilean system first formed, would the intensity of its reflected light suggest a much different volcanic output? The light of our own system is a local, condensed history, showing how energy and gravity sculpted raw material into a family of distinct, evolving worlds. The history of our home is written in the light reflecting off its immediate neighbors, a complex interplay of forces that has persisted for billions of years. The light from the center of the universe, the CMB, shows the residual imprint of acoustic oscillations in the early plasma before recombination occurred. If those sound waves determined the initial distribution of matter, what cosmic melody was played in that primordial moment that dictated the shape of all future light? The universe began with a vibration, a sound so profound that its echoes are still visible today, imprinted on the oldest light we can perceive. The history of the cosmos is not merely a story of light, but a symphony where the earliest notes, though silent now, are visually inscribed in the sky. The light emitted by a pulsar is a highly regular beam. Any deviation from that periodicity indicates a physical change in the star's structure or its orbit. If the light shows a sudden, slight change in pulse rate, does that light carry the history of a crustal shift within the neutron star itself? The pulsar's steady beat is a beacon of historical stability, but even in its regularity, we find evidence of internal, catastrophic revisions recorded in the signal. The history of extreme objects is one of violent internal rearrangement, where the light faithfully records the scars of crustal adjustments across millennia. The light from galaxies that have undergone minor mergers shows streams of stars being pulled out into long, faint tails across the intergalactic medium. If we trace those light streams backward, would they converge precisely on the location of the smaller galaxy, whose light we can no longer resolve individually? The light confirms that history is a process of gradual assimilation, where the distinct narrative of one system becomes diffused into the larger history of another. The true shape of a galaxy's history is visible in the ghosts of the companions it has absorbed, their light forever smeared into the larger structure. The light from the most ancient globular clusters indicates ages that challenge the current standard cosmological model's prediction for the universe's first structures. If the stars are truly older than the universe allows, does that imply that the rate of expansion in the very beginning was slower than we currently calculate? The ancient light presents a historical contradiction, a point where our interpretation of time clashes with the observed duration of stellar existence. When light testifies to a longer past than we have accounted for, we must listen carefully, for the universe may have a much deeper, older memory than we assume. The light from a solar flare, a sudden burst of energy, is emitted as charged particles interact with the intense, fluctuating magnetic fields of the sun. If we could observe the flare's light from 1 light-year away, would the emission spectrum show evidence of the time it took for the magnetic energy to resolve? The light records the energy cascade, showing how magnetic tension, built up over days, can be released in a brilliant flash that travels across space. Even localized events on a star are governed by cosmic rules, their history dictated by the speed limit that governs how quickly the released energy can inform the outside. We stand here now, illuminated by the patience of photons that began their journey before the continents of Earth had found their current shapes. We are not merely in the present. We are immersed in a sea of arriving history, breathing the light that left its source eons ago. The profound melancholy of astronomy is realizing that every object we admire is already irrevocably part of the past, forever slightly out of reach. Yet, in that very distance lies the beauty. The history is preserved, unblemished by our touch, offered to us as a perfectly focused memory. What is our role, then, but to be the conscious recipient of this light, the mind capable of translating the geometry of photons into the narrative of meaning? To observe is to participate in the universe's memory, to allow the long, slow story to finally find articulation in our own brief moment of awareness. We can never catch up to the light, but we can learn to respect the immense effort it took for that light to travel across the void on its lonely voyage. The universe whispers its biography through the steadfast arrival of its ancient beams, demanding only our attention in return for its infinite expanse. We look out, and we see not what is, but what was, and we are transformed by the patient evidence of time itself etched into the spectrum. Let us hold this knowledge lightly, that our present is built upon a foundation of distant, luminous memories, forever unfolding in slow motion around us. The light from a distant galaxy cluster, when mapped precisely, shows a gravitational potential consistent with the standard Car Lambda CDM cosmological model predictions. If the light reveals this consistency across such a vast reach of time, does that confirm that the fundamental laws have remained utterly unchanged since the first light? The stability of the laws, as recorded in the ancient light, is the universe's greatest gift. The assurance that our present deductions about the past hold true validity. Consistency across time is the silent promise that the universe's narrative, however long, is governed by an unwavering, singular set of principles. The light emitted by a pulsar that passes near a black hole will show a time dilation effect, slowing down the apparent period of its pulses. If the light pulse is slowed by half its expected rate due to gravity, does that mean the history of that pulsar is being experienced by us at half speed? The history passing near a singularity is stretched out, forcing us to observe its rapid processes in an extended, contemplative duration. Gravity distorts time itself, and the light that escapes records that distortion, showing us that time is relative to where one stands in the cosmic landscape. The light from the stellar component of an X-ray binary system shows a Doppler shift consistent with orbiting a dark, unseen companion star. If the unseen companion is a black hole, does the light from the visible star carry any spectral distortion caused by the extreme tidal forces exerted across the vast distance? The visible star's light is a proxy, a faithful recorder of the invisible companion's gravitational influence, tracing the path of that unseen mass across the past. The light makes the unseen visible, not directly, but through the subtle, persistent way that mass shapes the trajectory and energy of its passing neighbors. The light from the accretion disk around a stellar mass black hole is highly Doppler shifted due to the gas orbiting at a significant fraction of the speed of light. If we could isolate the light from the approaching side versus the receding side, would we see a clear, instantaneous division in the observed spectral lines? The light reveals the speed of destruction up close, showing matter being flung outward while simultaneously spiraling inward at incomprehensible velocities. The history of matter near the singularity is a history of transformation, energy converted into light at the very moment the mass yields to oblivion. The light from the earliest massive stars, had we seen it, would be characterized by emission lines only from hydrogen, helium, and perhaps trace lithium. If the universe had formed without those massive stars, the light of later galaxies would be almost entirely featureless, lacking any heavy element fingerprint. The light of those first giants, though forever lost to us, provided the necessary chemical vocabulary for all subsequent cosmic narratives to be written. They were the first authors whose brilliant, brief existence seeded the universe with the elements required to form everything we observe in the light today. The light from the sun, when analyzed near the terminator, is scattered by atmospheric aerosols, revealing the density profile of the upper atmosphere. If we could track that light over a period of great planetary upheaval, would the aerosol signature in the light show a rapid, historical increase in density? The subtle filtering of our own star's light carries the history of our atmosphere, a chemical diary written in the light that barely makes it through. The story of a world is written in the manner its local light is altered, the evidence of its atmosphere, its oceans, and its slow, evolving state. The light from distant gamma-ray bursts, though fleeting, provides an endpoint measurement for the expansion rate of the universe at that specific time. If the redshift from a GRB is significantly higher than the background light at that epoch, does that imply a localized, rapid acceleration event occurred? The light from these violent endpoints offers crucial data points, confirming or challenging the smooth historical progression implied by the background glow. The universe records its most catastrophic moments with the brightest, most easily measurable light, ensuring that even its most violent acts are not forgotten. The light from a distant galaxy shows that its star formation rate peaked approximately 10 billion years ago, suggesting a more active youth. If the peak has passed, Does the current light show a transition toward a history dominated by the aging of its existing stellar population? The galaxy's light reveals its life cycle, a phase of vigorous stellar birth, giving way to the long, reflective twilight of mature, aging stars. The history of all structures is the same: a brilliant, energetic beginning, followed by a slow, inevitable descent into the quietude of established age. The light from the edge of the solar system shows that the Oort cloud objects are largely static, having been gravitationally nudged by past galactic encounters. If we could track the light from those objects over centuries, would the subtle motion reveal the historical influence of nearby stars passing through our region of space? The light of the distant frozen remnants holds the history of gravitational encounters, the silent, powerful nudges that shaped our own planetary neighborhood. Our local history is not isolated. It is recorded in the way the light from our oldest objects has been subtly redirected by visitors from the galactic tide. The light from a distant star, when filtered through a dense cloud of molecular hydrogen, shows the characteristic absorption profile of reaching text $2 gas. If that hydrogen gas cloud is a relic from the early universe, does the light passing through it confirm that molecular bonding was possible at that ancient temperature? The light records the universe's slow progress toward chemistry, showing the point at which simple elements learned to bind together to form the first complex structures. The transition from atomic simplicity to molecular complexity is a key historical chapter, written in the subtle absorption patterns found in the light. And so, we return to the mirror of the night sky, feeling the weight of the ages pressing down on the fragile present we inhabit. We are creatures of the twilight, standing precisely between the luminous memory of the past and the unknown expanse of the unlit future. The ancient light teaches us that our brief sentience is a rare and precious alignment, a moment where the universe pauses to observe its own long history. Perhaps the ultimate purpose is not to solve the mystery, but to fully inhabit the quiet awe of witnessing a history so much vaster than ourselves. We do not own this light. We are merely its temporary caretakers, charged with translating its silent chronicle into a language that honors its journey. The true conversation begins when we stop demanding answers and start listening to the poetry inherent in the simple fact that the light still arrives. Let the vastness not create fear, but a profound sense of belonging to something immense, something whose memory stretches back to the very first moments. We are the fleeting observers, the brief interval where the universe's light gains a consciousness capable of appreciating its own antiquity. So let the stillness settle upon you. Acknowledge the ancient travelers arriving from the darkness, and carry their quiet message into your own fleeting day. The light continues its journey, long after we are gone, seeking the next mind capable of reflecting on the beauty of what has already been. The light from a distant quasar, spanning billions of years, reveals a history where the universe was dense enough to foster rapid central black hole growth. If that rapid growth history is accurate, what external forces prevented such explosive formation from dominating the universe throughout its entire subsequent lifespan? The light shows a phase of intense, youthful activity that eventually subsided, yielding to the slow, steady evolution we perceive in the calmer, later epochs. The narrative arc of the universe is one of high-energy infancy, giving way to a long, reflective middle age, illuminated by the echoes of that initial fire. The light from an X-ray binary system, when analyzed, confirms that the accreting matter is heated to millions of degrees before crossing the event horizon. If that heating process is so violent, what happens to the historical chemical signature of the doomed companion star as it is shredded into superheated plasma? The light records the moment of ultimate annihilation, the brief, intense, final chapter where all structure yields to the gravitational dominance of the void. The last light of a consumed object is the most spectacular, a final, brilliant proclamation of its existence before being forever silenced by the boundary of knowledge. The light from the sun's corona, viewed during an eclipse, shows the characteristic emission lines of highly ionized iron, indicating temperatures millions of degrees higher than the surface. If the light records this immense heat disparity, does it imply that the magnetic field shaping the corona has been historically unstable, fluctuating violently over time? The light reveals the sun's hidden energy, showing that the calm face we see is sustained by an invisible, turbulent history playing out just beyond the visible edge. The history of a star is not just in its continuous glow, but in the intense, energetic secrets it keeps hidden in its near-invisible outer atmosphere. The light from distant, newly forming galaxies shows a strong ultraviolet signature, indicating a population dominated by short-lived, massive blue stars. If those massive stars lived only a few million years, how quickly did the universe move through its first generation of chemical enrichment before the present light began? The early light speaks of speed and intensity, a history forged in rapid cycles of birth and death, accelerating the universe toward chemical maturity. The light confirms that the story of complexity began with ferocious energy, a rapid-fire sequence of creation designed to quickly populate the empty canvas. The light from a terrestrial meteorite reveals the presence of organic molecules, suggesting that the building blocks of life are widespread throughout the solar system history. If the light signature of these molecules is similar to those found in distant nebulae, does that imply life's chemistry is an inevitable product of universal light interaction? The light connects the chemistry of the most distant clouds to the material found beneath our feet, unifying the history of the universe with our own local origins. The history is one of chemical continuity. The elements forged in ancient stars are the same elements that now struggle to organize themselves into conscious awareness on this small world. The light from the CMB shows that the gravitational potential wells responsible for galaxy formation were incredibly shallow immediately following the inflation period. If the initial wells were so shallow, what sustained the steady accretion of matter over billions of years to form the immense structures we see in later light? The light implies a history governed by relentless patience, where tiny initial advantages were amplified over immense timescales through continuous gravitational gathering. The history of structure is a testament to the triumph of slow, persistent accumulation over the forces that continually work to dissipate that structure. The light from the most massive globular clusters suggests they formed very early, potentially during the epoch when the universe was only a few 100 million years old. If these ancient stellar collections already existed, what large-scale structure formed them? And what did their light look like before the Milky Way even began to coalesce? These clusters are islands of primordial history, their light representing the stable, early architecture of the universe before the major galactic collisions began. They are the silent historians of the galactic dawn, their steady, old light offering an uncluttered view of the foundational period of structure formation. The light from distant galaxies shows that the process of galactic mergers, which builds massive systems, was highly efficient in the universe's past. If mergers were more frequent, then does the light from the resultant galaxies show a history dominated by violent restructuring rather than slow internal evolution? The early light paints a picture of dynamic chaos, a time when structures were constantly being torn down and rebuilt through grand gravitational encounters. The history of the universe is a cycle of building and collision, where the brightest light often marks the aftermath of gravitational chaos reasserting order. We realize, looking back across the epochs revealed by light, that our present stillness is a rare, temporary pause in a history defined by ceaseless, luminous activity. The calm we seek is only found in the vastness between events, not in the events themselves, which are always marked by tremendous expenditure of light and energy. We are the beneficiaries of this long, luminous history, the temporary consciousness existing at a point where the echoes are still clear enough to decipher. Our deepest privilege is the ability to look backward, to commune with the past through the steady, faithful messengers that have traveled so far just to reach us. We still do not know if the light carries messages or merely memories, but that distinction matters less than the shared, profound experience of receiving it. Perhaps the universe does not intend for us to solve its history, but simply to witness it, to hold its light in our minds for a fleeting moment. The ancient light continues its journey outward, forever broadcasting the events that built the stars, the elements, and eventually the minds that look back. And so we watch the slow arrival of the past, accepting that the universe's memory, carried in light, is the most beautiful story we will ever know.